Welcome, everybody, to Standing For Truth. My name is Donny Budinsky, and it is my privilege to serve as your host and moderator for tonight's formal debate. Tonight, we examine a question that lies at the heart of geology, and the question is, what is the proper perspective of Earth's geology? Does the evidence point to the conventional plate tectonics and old Earth model, or does it better fit the hydroplate theory, a specific model of the global flood, and what the biblical account says about the worldwide flood? Representing the plate tectonics or old Earth position is Dr. Howard Feldman. Representing the hydroplate theory and a worldwide flood is Brian Lauer. As always, our goal is a respectful, evidence-based discussion where competing historical models are presented, examined, and challenged. We encourage everyone watching to follow the arguments carefully, engage with the evidence, and send in your questions throughout the debate. Gentlemen, I am pumped for this. I think this is going to be a technical, informative, and thought-provoking exchange on such an important topic. But before we get into the opening statements, let's break the ice a little bit. I'd like to get to know you gentlemen a little bit, especially for the audience sake, anybody who might be new to this channel and new to these kinds of debates. So it's always great to have fresh faces, new debaters on the Standing for Truth debate platform. That would be you, Dr. Howard Feldman. You're certainly no stranger here. We've chatted in the past, but it is your first time here on the program. So let's start with you just in terms of a brief introduction. Firstly, thank you for the time you've offered for this. And
well,
secondly,
thank you.
Tell us a little bit about yourself.
Yeah, thank you for allowing me, because I've been asking for this for a while now, so I really very much appreciate it. So I grew up in Buffalo, New York, where I really knew I wanted to be a scientist from the first grade on. And that's been the goal of my life, which I've succeeded in. I got a bachelor's in biology and geology from Oswego, New York. And then I got a PhD in paleontology from Indiana. I spent 7 years in the petroleum section of the Kansas Survey. And then I spent 26 years, most of my career at Exxon as a stratigrapher. I was hired as a stratigrapher in the stratigraphy research group. And then I bounced around the company an awful lot for 26 years. I retired a few years ago, semi-retired. I'm currently in Fort Collins, where I'm doing research. I'm consulting. Most of my consulting is teaching people how to do stratigraphy, how to recognize depositional environments. And I'm doing some publishing. I've got a couple books out. And yeah, I'm very happy to be here and to present the scientific side of things, which I hope we'll see how it goes.
Dr. Feldman, thank you for that introduction, helping us to get to know you a little bit. Feel free to send me the links to those books. I'll make sure that your books and any other references that you'd like people to see, I'll make sure those are in the description box of the video for those that want to see more from you. So I appreciate it, and I'm pumped for this. Brian Lauer, certainly no stranger to debates nor this channel. It's great to have you back, Brian. How are you today? And also tell us a little bit about yourself and your ministry.
Well, I'm doing great, Donnie, and it is such an honor and a privilege to be able to present a theory that makes accurate predictions, and it's being validated by NASA discoveries. But full disclosure here is I don't have a PhD. I'm not a rocket scientist, but there are hydroplate proponents that have those qualifications. They didn't step up to the microphone, and so here I am. And I've got I'm here because I think this conversation needs to take place. I think it's important for theories to their strengths and weaknesses to be publicly critiqued. And it's surprising how difficult it's been to have that happen. So Dr. Feldman, I appreciate your participation in this. And it's been a lot of fun. You know, one of my main passions is to give people an opportunity to think. And you need to see two sides of a situation if you want to think. And that doesn't happen typically in classes or even in society. And so, yeah, we just throw all the information out there. And I encourage people not to believe something because I say it or what Dr. Feldman says, but just check out what we're saying to see if it's true and then come to your own conclusion. And yeah, I think we need more thinkers in our society. And I've got a YouTube channel called Solidify Your Faith. And I like to go wherever God opens the doors, whether it's at church, colleges, schools, conferences, wherever. And we've been praying for open doors. And then you emailed me and said, does anybody want to debate Dr. Feldman? And I run it up the flagpole and nobody did. So here I am. And I'm looking forward to this. And thank you for putting it together. And thank you, everybody, for viewing. And thank you, Dr. Feldman, for participating.
Brian, thank you for that introduction. I respect anybody who's willing to step up to the mic, enter the debate coliseum for what I think are important exchanges. We really do need to get out of our echo chambers, whether it's scientific echo chambers or theological echo chambers. We host a lot of debates on those topics as well. And so for that reason, Brian and Dr. Howard Feldman, thank you so much for the time for tonight, but also the time leading up to the debate itself. I know it requires a lot of work and effort. So thank you very much. For those that want to see more from Brian, I've got his channel linked in the description box for people to check out. Okay. And in our live chat, Scriptures in Stone says, awesome debate topic. I completely agree. We're doing this live. So as people make their way in, as we move towards our opening statements, reminder, what we're debating tonight is this. What is the proper perspective of Earth's geology? Dr. Howard Feldman holds to the plate tectonics, old Earth view, the conventional model. Brian Lauer, the hydroplate theory. Let's make sure we're on the same page, go over the format. So format for tonight, we've got a comprehensive one, which I think is necessary for a debate of this magnitude. 20-minute opening statements, starting with Dr. Howard Feldman. Then we jump into uninterrupted rebuttals. We've got 10 minutes to respond to each other's points and arguments brought up in the 20-minute opening statements. Then we jump into a discussion, which is structured as more of a cross exam. So it'll be fast-paced, 20 minutes each, where both debaters, Dr. Feldman and Brian, get that opportunity to pick the topics, ask the questions they feel are most important. Then we jump into closing statements, 5 minutes each, good opportunity to wrap up our thoughts, wrap up our points, as I'm sure by that point, there's going to be a lot on the table for sure. Then we get to hang out with you guys for roughly 30 minutes. We'll be engaging in an audience Q&A period. So please, if you got a question, a challenge, tag me at Donny or at Standing For Truth. That way I don't miss your question. Let's be professional. Let's be cordial. No attacks on the debaters as they've been so gracious with their time. And what I'll do is bump super chats to the top to guarantee that those are engaged. Okay, gentlemen, 20 minutes in opening statement form do fly by. So what I'll do is give a 1-minute warning as you guys are presenting. When you hit that 19-minute mark, I'll say 1 minute. That way you'll know to start winding things down. Dr. Feldman, whenever you're ready and comfortable, you can get your screen shared and I can put that up for the audience to see. And we can move into our first opening statement. Okay, I see it here.
You should see it now.
Good. Yes, looks good. And you feel free to present whenever you're ready, Dr. Feldman.
Thanks. So first, thanks for letting me here and have my say. So here's a couple of books I've got out. The left one is pretty expensive. It's on stratigraphy. It's how professional petroleum geologists do stratigraphy. The one on the right is more of an introductory text, and it's about how you go about interpreting siliciclastic rocks. Siliciclastics are sandstone, shale, and conglomerate. That's siliciclastic. So it doesn't include limestone. And you can follow the QR code, and that'll get you to the bookstore. So here's a general diagram of plate tectonics. In 20 minutes, I'm not going to introduce everything. I'm just really going to talk about the Mid-Atlantic Ridge. And so this is the standard plate tectonics view. There's an awful lot of data that supports this that I would contend hydroplate theory needs to ignore in order to accept that theory. And I'm going to present a lot of data. I suspect some of the data I'm going to present you've never seen before. So we've got to start with a little bit of a definition for tectonics in the petroleum industry. And in tectonics, we talk about active margins and passive margins. So an active margin is the boundary of a continent that has a lot of earthquakes, mountains, volcanoes, that kind of thing. And a passive margin is the opposite, where things are very quiet and sediment is just accumulating. Typically, the big rivers empty out into passive margins. So all of the Atlantic up and down is a passive margin, and typically the other side of, say, South America and North America is active. So I'm going to, yep. So this is what a typical seismic line looks like through an passive margin, except, whoops, That was not what I wanted to do. You know what? I just messed up. Let me try this again. I'm trying to adjust the pointer.
Dr. Feldman, that's why I work here, and that's why
Yep.
they pay me the
There
big
we
bucks.
go.
So if something happens, no worries.
Yeah. So
I think you still got to get your screen shared, though.
Did I unshare it?
Yes. No worries, though. And Brian, we know you're still here. I've got the presenter on screen at all times, and then I put us backstage. So
I apologize for that.
Oh, no worries. That's okay.
Totally my fault. This is a typical seismic diagram of a passive margin. I want to describe what that is. Absolutely everybody listening has seen a seismic image. They just don't call it that. If you've ever seen an image of a fetus or a baby inside a pregnant woman using a sonogram, that's what we mean by seismic in petroleum. It's using sound waves to create an image, except we use dynamite, not, a little handheld device. But it's exactly the same concept as a sonogram in medical devices. This is a ship that typically is used, and they'll tow a cable behind it. There'll be a mechanical device that produces the sound waves. And then there'll be a cable stretching out maybe up to 15, 16 kilometers. And it produces an image. This is old data from the 1980s probably. And it shows what a shelf edge looks like. And this is pretty common up and down the Atlantic coast. So we've got continental crust here. We've got oceanic crust there. We've got 5 kilometers of sediment. And then here's the shelf edge. The idea is that at low sea level, when the glaciers formed, sea level is lower, the rivers went to the edge of the shelf and they created deltas. That's how the shelf edge grows. But notice there's all these deltas here. Right. So this shelf edge is a depositional feature from sea level going up and down many times. And how did sea level go up and down many times? Well, it's from glaciations. So this diagram from Dr. Brown's book bears no relationship to the data. And anywhere in the world that I know of, it shows a very, very thin sediment cover that doesn't exist anywhere that I know of. And this is what typically exists. So when we look at what is the boundary of a continent to an ocean, it's continental crust to oceanic crust. That's the boundary, which I'm showing here in 2 different colors, kind of pinkish and blue. So now we're going to look at another section up here, and all this data is collected for the petroleum industry. So So there's all the different shelf edges. So you can see the shelf edge moves back and forth due to sediment supply and sea level history. Now, when the shelf edge was down here, we're not saying the sea level was like 3 kilometers below where it is now. It's the whole thing has subsided due to the weight of the sediment. But that does take millions of years. You can't do it really faster. So that's the first problem for hydroplate, is explaining that. And none of this looks like liquefaction. So here's another section. Now we're in northern Brazil, and we're looking at an area out here. The shelf edge is way to the left, but this is where the continent oceanic crust boundary is. This is from a publication by several of my colleagues at Exxon. So you see oceanic crust in green. I conveniently changed the colors, and then continental crust in pink. So there's several things to look at here. First is the moho, which is the boundary between the continent and the mantles. It's mantle lithosphere versus the continental oceanic crust. This crosshatch pattern in seismic is pretty typical of oceanic crust. Typically, oceanic crust is about 6 kilometers thick. These are in kilometers here, and this is 10 kilometers there. So there's no vertical exaggeration here. And then there's oceanic crust here, a type called SDR crust that actually onlaps the continents, which isn't part of hydroplate theory. And then several kilometers of marine sediment. If you go to the shelf edge, which is out here, which is about 30 kilometers to the left in this diagram, that's not where the edge of the continent is. That's just a purely depositional feature. And you can compare that to what we see from Dr. Brown's book. So the first thing is he doesn't have any sediment covering the edge of the continent, which isn't true. There's several kilometers of sediment. He's got a very thick continental crust here with almost a flat bottom, which isn't true because the bottom is isostatically adjusted. So you can think of it like an iceberg. The bigger the iceberg, the lower down it sits in the water column. Same thing with the crust on the mantle. He's got this porous mantle there, which doesn't exist because we've got tons of data that goes through that part of the section from earthquake waves. And so we know with high degree of confidence that doesn't exist. These water pockets, they don't exist because they would block shear waves. from earthquakes, and you'd have a shear wave shadow on the continent, and that's never been observed. The deepest hole that's been drilled is about 10 kilometers, which would be about that. If this is 30 kilometers, there's no scale here. And so there's basically nothing about this diagram that's realistic, that's consistent with the data. And so Dr. Brown says actual continent boundary is generally considered to be halfway down the continental slope. That's not true. Politically, that's true, from a political boundary, but geologically, that's not true. And then he says this is a typical shape of an ocean continent boundary worldwide. That's not true. There's no place in the world I know of that looks anything like that. And so he's got everything wrong. And these data are not new. I mean, this kind of data has been published for decades. So there's nothing about that diagram that is consistent with the data that we have. So here's a diagram from Brian Nichols' YouTube series. He's got this a little bit better. At least he has some basaltic crust there, which the other diagram didn't have. It just went straight to mantle. But he doesn't have any sediment in here. So this is, these are the kinds of diagrams somebody would draw who had never taken a geology course, which I guess is true, right? They've never taken a geology. This is the value of getting a geologic education, is you learn this stuff. And so we've known from the 1970s that there was a thick accumulation of sediment, and that's what's forming the continental shelf boundary. So nothing in this diagram is true, other than there's a little bit of basalt here. That's accurate, but nothing else. So that's not true. So now let's move on to the Mid-Atlantic Ridge, which is really what I want to talk about. And so this is the diagram from Dr. Brown's book showing the continent sliding away. So let's look at what the Mid-Atlantic Ridge actually looks like. This is a cross-section I just took from Google in this location, kind of in the middle of the Atlantic. This is vertically exaggerated. That's 500 kilometers. There's 3 kilometers, 4 kilometers. It just gets 5 kilometers deep there. So typically about 3 kilometers of relief from the highest point in the Atlantic to the lowest point. But the slope is 0.24 degrees. It's not this. It's nothing like that. And the maximum thickness from here to there is about 3 kilometers. So this shows a 1 kilometer thick continental crust. It's 30 kilometers thick. So you'd have to multiply that times 10 just to get in the ballpark of what the realistic thicknesses are. And there's no evidence of this kind of arching and these kinds of cracks. They don't exist. And so nothing about that diagram is correct. So this is what, So this is what the cross sections actually look like if you look at all the cross sections of the oceanic ridges. So the reason this is important is because the hydroplate theory model, and I'm waving with my hands, which you can't see, but you just have to trust me. The hydroplate model says that the Atlantic ridge popped up as Africa and South America and North America moved away from each other. All right, well then what moved away from C? Why did this pop up the same amount? Or D, or E, or F, or G? What continent moved away from F to allow that ridge to pop up? It's a little bit less. It's not quite as much relief. It's only about 2 kilometers rather than 3. But still, none of it makes sense. What really does make sense is it's all due to a single mechanism, which is seafloor spreading. So here's another test of the model. This is a map of the mid-oceanic ridge. There's Africa and South America. And there's these transform faults here and here. So I've just drawn in red the mid-ocean ridge. And then we're looking at the transform faults. The big question is, how did they form? So in the 1960s, there was a big question about this. One is that you had a standard model that I show in the upper left here, where like a road going through across the San Andreas Fault, it's just shifted to the left. And so you have an arrow to the left here and to the right there. And this is in map view. And the other is that there's actually new crust being created here. In which case, this plate is moving this way, this plate is moving that way. So beyond the red lines, the plates are moving in the same direction, or the blocks of rock are moving in the same direction. So there's no relative movement here. And so that would result in 2 very different earthquake patterns that were predicted before they were measured. And so you'd only get earthquakes which record movement in between the red lines. And so what did they find? They found earthquakes in between the red lines, exactly as predicted. So as far as I know, there's no mechanical solution to this other than seafloor spreading. I don't know how else you would do it, because there's earthquakes in between the red lines, but not beyond, even though the faults extend for over 1,000 kilometers. But they went beyond that. If you notice, the direction of motion here is to the right and here it's to the left. They were actually able to use shear waves and show that the direction of motion is as predicted for plate tectonics and not this. And so how do you get around this? Well, I think for hydroplate, Dr. Brown doesn't even mention this data set, which is highlighted in every textbook. So how do you get around that? I don't know. I mean, the only solution that we know of is that the seafloor spreading is taking place at the red lines. And let's also remember that in the 1960s, they predicted the Atlantic Ocean was getting wider. And then a couple decades later, they measured it, and it is, in fact, getting wider. Well, if it's getting wider, there must be new crust being created someplace, and it's in these mid-ocean ridges. So here's a new data set. The earthquake data set just gets better and better and better. So there's no relative motion to the faults beyond the spreading centers, and they are spreading centers. There's actually submersible movies you can find on YouTube where they've gone down in submersibles, and they show that at the mid-ocean ridge, there is new basalt that is being created, a type of basalt called pillow basalt. So now let's go to the magnetics. This has been widely described by creationist literature, almost always incorrectly. So the correct view of this is that in the early 1900s, 1906, it was discovered that successive lava flows had 180-degree reversed magnetic fields preserved inside the lava flows on land. And not much was done until after World War II. And then there was an explosion of studies. And this study in 1964 summarizes all those previous studies. And what they showed is there's a lot of lava flows around the world where you have a few lava flows with one magnetic orientation, then a few with a 180-degree switch, and then back to normal, and then switched. And they reviewed all the different explanations for that. And the only one that's consistent with all the data is that the Earth's magnetic field has reversed many times. And since then, there have been many more studies of lava flows on land. And so they already knew that the Earth's magnetic field had flipped from all the lava flow evidence on land. And so that's why they went out and they measured this. Now, they couldn't actually go down and sample the seafloor in 100 different places, too expensive. So they measured it on the surface of the ocean. Actually, this is an aerial survey. So they're a few kilometers above the basalt. And so the idea is where the basaltic crust is the same orientation magnetically as the modern field, they add together, you get a slightly stronger field. And where the basaltic crust is reversed, it subtracts, and so you get a slightly weaker field. And so this is exactly what was predicted, and it's symmetrical. And the problem for hydroplate theory is wherever there's a spreading center in the Pacific Ocean, in the Indian Ocean, you get the same magnetic stripes. So this is a magnetic stripe data from the USGS. And so what's the explanation? Well, the explanation that actually fits all the data is that the Atlantic is getting wider, new crust is being created, and it's recording the reversals of the magnetic fields, which we've seen now. There's tons of cores to this now. So we know that these samples are preserving full reversals. So, Brian Nichols has a explanation to have to do with the cracks and things, and that explanation, I would say, is, to be blunt, is uncontaminated by evidence. And there's tons of evidence from cores. There's no excuse for not having evidence. So we know these are reversals in the preserved magnetic field in the rocks. It's been observed in core. And so I don't know how you get around not having the Atlantic getting wider and not having the reversals of magnetic fields. So now let's go to the fit of the continents. Dr. Brown likes to criticize this diagram, even though it's from 1965. There's much more recent diagrams. I'm sorry, I'm just checking the time to make sure I'm still on schedule. So yeah, it's not a great fit because Bullard, when he did this diagram, he used the continental slope as the boundary, which he knew at the time wasn't correct, but it was the best they had at the time. So here's the Niger Delta. He even says in the paper, we know this delta is much younger than when the continents were together. So obviously that lack of fit doesn't work. But what I really want to talk about is this statement that I've seen repeated many times, that Africa was shrunk by 35%. And, you look at the size of the squares here, maybe that looks correct. That is not true. I mean, I just don't understand how somebody in good faith, without knowing that they're lying, would make that statement. And he even Bullard even addresses this in his paper. He says, I know it looks like the continents have been changed in size, but they haven't. It's an artifact of the Mercator projection. So I sacrificed a globe. I sacrificed a globe just to prove this point. So here I cut out Africa and I put it next to Australia, or next to South America. So look at this point here is that point there. I've colored in the equator here. And if really Africa was 35% too big, it wouldn't fit. It would be, the toe of Africa would be like down here, but it isn't. It fits exactly the same as this diagram. Now, it's not exactly the same. This is a child's globe from when my stepkids were kids. But you get the idea. This is false. And if your theory is based on false statement after false statement after false diagram, what's it worth? I mean, nothing, very little about the geology in this book is actually correct. So let's go on and look at some modern diagrams. What people use nowadays is the boundary between continental crust and oceanic crust, not the shelf edge. All those diagrams of the shelf edge in the book are completely false. And so here's the boundary that's used today. These are a couple papers. These are open access papers, which is why I can show them. There's no copyright restrictions. But what's really interesting here is that the way Africa and South America split, they didn't split like this. They actually rotated, they unzipped. And so as the Atlantic Ocean was being created, there's this huge salt basin that was created. And you can see it here in this paper too. And so what was happening is the basin was closed to the north. There was evaporation that exceeded the amount of seawater that could come in. There's actually a sill called the Walvis Ridge, which prevented open access to seawater. And so today, what we look at is here's the salt there. There's the salt there. What's the hydroplate explanation for this salt? Well, they ignore it like they ignore so much data. You have to ignore an awful lot of data to accept the hydroplate theory. So here's a cross-section here. Notice it looks nothing like the cross-sections of the continent-ocean boundary. The oceanic crust boundary is just beyond the edge of this cross-section. But here's the salt, 14,000 cubic kilometers of salt. You could hardly say that's trivial. And there's sediment above it, sediment below it. This has all been drilled for hydrocarbons, so we know that this exists, and we know that there's sediment below it. So what's this hydroplate story here? You have several kilometers of sediment, then the salt, and then several kilometers more sediment. So the only explanation I know of that actually makes sense is that Africa and North and South America were next to each other, and there was a narrow basin, and then the pieces of salt actually fit back together. And so I think that is a much better model for how this system works. And this is just the tip of the iceberg of the data that you have to ignore in order to accept the hydroplate hypothesis. So if we look at the way the continents actually look, this is a cross-section through the continents to scale. It's vertically exaggerated about 3 times. It's from a video series by a German guy, but there's English translations. Sorry, that's my alarm telling me that I'm about over time.
Dr. Feldman, feel free to take 30 seconds just because I did pause your timer when we had that little hiccup. So
okay,
feel
thank
free
you.
to finish your thoughts. No
so this is the summary of this. This takes into account all the evidence from earthquake waves, both shear waves and P waves. It takes into account all the gravity measurements, which I haven't really talked about. It takes into account isostatic equilibrium, and it takes into account the direct imaging we have from seismic. So that's why we know that the Moho goes down. It's not flat. We know that the mountains have deep roots from gravity measurements. And so if you add up the weight of all the crust here and the weight of all the crust there, it's the same. So just like an iceberg doesn't displaces an equal amount of water to the mass of the iceberg, the same thing with mountains. So like the Himalayas, they don't add any mass to a certain area because it's exactly equilibrated by sinking down into the mantle. And the first gravity measurement of the deep roots of the Himalayas was done in the 1890s. It's not like this is new data. So this is what this cross-section through the crust and the lithosphere actually looks like if you include all the data. So there's so much more data that I could present. I'm going to stop here because I know I'm out of time. But this is why the Himalayas don't add mass to and they're not going to affect the rotation of the Earth. By the way, if you take I'm just going to say one more thing. If you take the Earth and scale it down to the size of a bowling ball, as you like to do, Brian, the Himalayas will stick up 1/1000th of an inch above the surface of that bowling ball. That's how big they'll be scaled down to that level. They will not affect the rotation of the Earth. It's absurd. And they're balanced by sinking into the mantle. So I've got lots more data to present, and I haven't even gotten into stratigraphy, but I'll stop there because I'm out of time, and thank you for the opportunity.
Dr. Howard Feldman, thank you very much for that opening statement and those opening arguments. To our audience, thank you for the engagement and interaction so far. I am caught up on your questions. I know it's a technical topic, so again, if you have questions of clarification, challenges, objections throughout our program here, we will be hanging out with you for about 30 minutes for an audience Q&A when we're done with our main session. So keep those questions coming. And Brian, to be fair, we'll give you equal time, of course. So take roughly 21 to 22 minutes for your opening statement. I see your screen shared at the bottom. I'll pull it up. Just make sure to unmute before you speak. And I will hit your timer when you're comfortable to present. As you work your way towards, oh, there we go. Yeah, we're
Okay.
good.
So now we're good. You can hear me and you can see me.
Yes, I can see you and hear you. You're coming in good, Brian.
All right. Okay, well, thank you so much. And tonight we're going to talk about how the features of the Earth got there. So let's take a look at some of the features. We got the Mid-Oceanic Ridge, which is a mountain range that goes through the bottom of every ocean, and it's 46,000 miles long. And it's made by stretching it in two directions. When you have a tension, when rock is in tension, when you're trying to pull it apart, it's going to break at the weakest point, and then it's going to crack along the straight line. And you'll see in this here, it's got vertical and horizontal cracks. You've also, and that's different than compression cracks. This is the Gunnison Canyon, and it's got 15-foot trees on a 2,700-foot cliff, and that granite has been squished together. Those are compression cracks. We've also got diamonds, and that's made from pressure. That would be the equivalent of being under 75-mile-high column of rock in 1,600 degrees Fahrenheit. We've got mountain ranges that are parallel to the Mid-Atlantic Ridge. We've got plateaus next to that, a lot of them. We've got the 90 East Ridge, which is 3,100 miles long, and it's almost perfectly straight, pointing at the Himalayas. And that's got the Mount Everest up there, the highest point on Earth, 29,000 feet. And then we've got the lowest point on Earth, almost a mile deeper than how high Everest is. And that's the Mariana Trench, and that's in the middle of inside the Ring of Fire, where there's a lot of earthquakes and volcanoes, and 80% of the trenches are in the Western Pacific, and it's 40,000 volcanoes in the Pacific. And we've also got Zealandia. That's a sunken continent. And what does that have? They found evidence of land-based fossils on Zealandia. In the South Pole, fossils show that crocodiles, dinosaurs, and palm trees once lived there. And on the North Pole, it shows that there's snakes, tortoises, alligators, redwoods, badgers, shrews. They can't live in permafrost, and yet we find them in permafrost. Then we've got every layer that's out there, the so-called geologic column. Every one of their layers has saltwater creatures in it. And they found 80 fossilized whales in the driest desert in the world in Chile. They've also, in Peru, over 3,800 feet above sea level, they found hundreds of fossilized whales, plus ground sloths. And then we found a huge, massive dinosaur. This is Dreadnoughtus, about the size of a Boeing 737, that is pretty in good shape. I got almost all of it. So something had to bury that rapidly. And then there's a lot of frozen mammoths near the Arctic Circle, and one of them was frozen standing up. And then we've got inland seas. These are the Gulf of Mexico and the Mediterranean Sea, where there's 1,000 feet of salt underneath them. And then the Gulf of Mexico, there's 30,000 feet of sediment on a 1,000-foot mother salt layer. And sometimes that salt will start going up through the sediment, and they call those salt domes. And some of those are taller than Mount Everest. We've got the Grand Canyon. That's my favorite topic. I'll debate anybody anytime on this one. And before you can make the Grand Canyon, you got to have the Great Denudation. You got to remove 1,000 feet of sediment over 10,000 square miles. That's bigger than Vermont. You got to remove 2,000 cubic miles of that before you can cut the Grand Canyon. And this is a remnant of that. The Red Butte, 1,000 feet of sediment capped with volcanic rock. And then in Grand Canyon, you've got these bent sedimentary rock layers, and they're bent at 90 degrees, and they aren't broken. They aren't cracked. Okay, and then you got these Grand Canyon layers again. They just don't stop in the Grand Canyon. Not only are they continent-wide, they are worldwide. Tim Clary's done some excellent research. He's looked at 3,000 boreholes over 6 continents, I believe. And he's found these Grand Canyon layers all over. And this is another Mississippian and Devonian. That's all over the place too. You see them in the Grand Canyon, and they show up worldwide. And we've got slanted layers underneath flat layers in the Grand Canyon. And one of those slanted layers had a piece of it broke off, and it got raised up into the flat layer. And rock is 5 to 10 tons broken off of its quartzite, and then it got lifted up into sedimentary rock. And we've also got submarine canyons. These are canyons on the continental shelf that are average 3 miles deep and 50 miles long, and some of them are longer than Grand Canyon, some are deeper than Grand Canyon, and they're underwater right now. And we've got water gaps. That's where a river will flow through ridges instead of flowing around them. So this river cut through a 800-foot ridge. And then we got billions of round quartzite rocks on plateaus from hundreds of miles away in Wyoming. And we've got the Ice Age. And notice there's no glacier in parts of Alaska and Siberia during the Ice Age. Okay, and we had in 2019, NASA said they found the Earth's oldest rock on the moon. And they said that it was crystallized about 12 miles beneath the Earth's surface. We've got asteroid Bennu, which Bennu has serpentine, and that's formed when the mantle touches the ocean. Okay, so we've laid out a bunch of features on Earth, and what if one theory could tie them all together and also make logically explain it, make accurate predictions, and be validated by NASA discoveries? Question: should that theory be justified of studying it? Should people be able to see it? Well, we can thank Walt Brown for this theory. I think he's today's Isaac Newton. A sharp guy. He's got his PhD from MIT in mechanical engineering. He ran the Benet Military Lab. He taught at the U.S. Air Force Academy. And I had an earth science person say, just like Dr. Feldman said, well, he should have took geology. He's not a geologist. That's what the professor told me. And I said, yeah, that's right. He's not. He doesn't have the degree. But he did take geology classes, and he was taught by Dr. Bob Dietz, who won a Penrose Medal. And he met with them every Wednesday for a school year, and they'd bounce theories off each other, bounce ideas off each other, and then they'd go listen to a geologist speak that night, and they'd bring him out to eat, and they'd eat. So they'd eat with the geologist. So Walt Brown had access to the sharpest mind in geology at the time. This is the guy who coined the term seafloor spreading. So to say that he didn't have any geology is, I think, a little unfair. But anyhow, this theory, it's a cause to effect. Most theories you look at, they know what happened. They know what the effect is, and they try and figure out what caused it. And you never really know. But this is different. Walt Brown's going to set up the cause with one assumption. That's it. And then he's going to let the laws of physics go at it, and it's going to explain whatever, pretty much the effects that we see. So what's the one assumption? Half of the ocean was inside the Earth at one time. So just think of the Earth as a big apple. The crust is 60 miles thick. And underneath that, there's a layer of water about at least a mile thick. And then there's the mantle. Okay, that's the one assumption. And how do you throw the laws of physics in there? The moon. The moon's gravity tugs on the Earth, and we have high tide and low tide twice a day. And back then, it's tugging on the crust. And the crust isn't broken into plates like it is today. And so the crust would stretch and compress, and they generated heat. The water got hotter and hotter and hotter. It wants to boil, but it can't because there's no room to expand. And then at 705 degrees and 3,200 PSI, it becomes supercritical water, where liquid density equals vapor density. So it's not really water and it's not really steam, but whatever it is, it dissolves things like crazy. So now it's dissolving the granite above and the mantle below, and it's mixing it together to make stuff like limestone and quartz, which are excellent cementing agents, by the way, and also salt and chalk. And these minerals are precipitating out of the water. And so you're getting layers of the limestone and layers of salt and layers of quartz at the bottom of these subterranean chambers. And then the crust is getting weaker and weaker and weaker because it's getting dissolved, and the pressure is building up on that water. And Walt Brown says there's 372,000 psi on that water. So when that crust cracks, the water is just going to erupt out of there with tremendous force, and it's going to rip the crust of the earth in two directions, and it's going to come together, go around the earth, and come together like a seam on the baseball. And people say, "Well, if that happened, wouldn't it leave a mark?" And it's like, yeah, it did. It's called the Mid-Oceanic Ridge. This is the ridge is what was underneath the plates as they were exploding up there. And so now you got these 60-mile cliffs crumbling into this hypersonic water. And on Earth, you can only have a cliff 5 miles high before it crushes it below. So this is all crumbling in there. This is where we get the sediment for the sedimentary rock. And then the cliffs are getting wider and wider and wider and wider. And pretty soon there's nothing pushing up down on the mantle. So the mantle bulges. And even if it's a little bit, if it's friction free, it's going to start rolling just like a train track. How much do you have to lift up a train track before that train starts rolling? And once it starts rolling, it's hard stopping it. Okay, so you got North America and South America going to the west, and you got Africa and Europe going to the east, and then they keep going until they meet resistance. And then they buckle up like a rug going against a wall or a car, the hood in a car accident. It buckles up. And it didn't happen slowly. It happened quickly because there's no cracks in this. These are the folded mountains in British Columbia. And so then also notice that the mountain ranges are pretty much parallel to the mid-Atlantic ridge. Okay, and then the compression event. All this compression, you got one end of the plate that stops, while the other stuff is still going. And that's how you get those big compression events. You make the coal and the oil and the marble and the diamonds. So it's not a 75-mile. Oh, and also this stuff all has carbon-14 in it, which shows that it's less than 100,000 years old. Diamonds, oil, coal, all that stuff, fossils. And so the diamonds, they didn't have a 75-mile high column on top of them. They just had a 75-mile-an-hour plate that's getting crushed into them as the other end stopped. And then it makes these compression marks, and that's how you get 50 miles of a 2,700-foot cliff to crush. That's a lot of force there. And you got the same compression marks in the inner gorge of the Grand Canyon, the Vishnu Schist. And that's how you get these folded sedimentary rock layers in the Grand Canyon. And then as the basement rock buckled underneath the Grand Canyon, the layers that were on top of the basement rock, they went up too. And so now they're slanted. But the layers on top of them, they got a lot of momentum going. So they just shear off those slanted layers. And that's how you get flat layers on top of slanted layers in the Grand Canyon. And then some of that stuff, it busted off that quartzite rock, and it got lifted up into sedimentary rock. And you can see that at the Isis Temple there. And that's 5 to 10 tons. And now you got the mountains, which is a big mass on a small base. Well, if you got a big mass on a small base, it's going to sink in. Well, if something sinks in, something's got to rise up, and that's the plateaus. Okay, and the mantle's the mountains are sinking down, and the mantle's getting squished out to the side, and then it's going to block fault the plateaus up and not deform them. Okay, and so the mechanism for plateaus is hydraulic lifting, and the force is gravity. And engineers love this theory because it all makes sense. And then some of the magma it's block faulting some of them. It got to the top. And it got on top of this sediment. And then when the great denudation came through, when there's two huge lakes catastrophically draining, washing away all that stuff, but then that volcanic material on top protected it. So then it washed it away around it. And so we have a remnant of what was there before the great denudation. And so that's how you move 2,000 cubic miles. Okay, and then you got at the mountains, if something sinks in, something's got to rise up. Well, conversely, if something rises up, something has to sink in. And the mid-oceanic ridge was rising up, and that sucked in the Pacific Ocean. And that's why we got the Ring of Fire. That's why we got all the trenches there. That's why we got all those volcanoes there. There was a lot of magma that's how we got the Zealandia to sink in. And that now the world, which is covered by water at this time, that's how you're going to get seawater animals on all the layers of the column. And then it's also this is how you get billions of dead things buried in rock layers laid down by water. Enough sediment to bury a dinosaur. That's a lot of sediment, and that's not happening today. And this is a puzzle for paleontologists. And then the water that was covering the world, now the Earth, now gushes off the Earth to fill in the Pacific Ocean, and it's going to cut the canyons in the continental shelf. And then the continents sink in and the oceans rise up and bury the canyons in water. Okay, and some of the stuff was shooting up with such tremendous force that it, from the subterranean water, shot up with such tremendous force that it escaped our atmosphere, got into outer space and became super cold. And then the Earth's gravitational pull pulled it back down. So you got dry ice and frozen sediment up there, comes crashing down and buries the mammoths. And then one of them is buried standing up. And if you want to see all the information, that's what I'm all about. Get all the information and then think for yourself. You can go into creationscience.com and go to page 293, and you're going to see this decision table. All the theories for the mammoths are on the top, and all the features of the mammoth are on the side. And it's red, yellow, green. And then red means there's some serious problems with it. Yellow means there's some moderate problems with it. And greens means there's no problem with it. And if you notice under the hydroplate, it is no problem pretty much all the way down. Okay, so that's how you freeze the mammoths, but how come they didn't thaw out? Because mammoths are not Arctic animals. They're not woolly. They just have hair. And it's that they don't have oil glands to make it watertight. They don't have erector muscles to make it insulate. And they're fat. So there's a lot of food. There's a lot of food and a lot of water, but there's not a lot of food and water in the tundra, especially when it's dark 4 months of the year. So they're temperate animals. Okay, so how come they didn't thaw out? It's the big roll. Okay, and that's, you got the big mass. And again, it is a big mass. There's nothing canceling it out on the southern hemisphere. The big mass of the Himalayas, and then that's a big mass on a spinning object. That's going to it's going to try to get to the side. Okay, and when it tried to get, and it does, it gets to the side. And when it gets to the side, that means something from the side went to the top. And that's how you get Mammoth Bill. This is my favorite slide. These are Brian Nichols slides, a lot of them. Mammoth Bill goes up to Mammoth Chill. You know, that's where they're fat and sassy, where it's temperate, and they're fat, and then they go up to Mammoth Chill, and they never thaw out. And people say, well, if that happened, wouldn't it leave a mark? And it's, yeah, it did. Oh, yeah. But also, it also brought up there to the Arctic Circle, you got snakes, tortoises, alligators, all that stuff that can't grow in permafrost or in the dark, or redwoods can't grow in the dark. It brought it up there. It didn't live there. And that's how you get palm trees, tropical palm trees in the South Pole. And if it wouldn't it leave a mark? And yeah, it did leave a mark, because the Earth isn't round. It's got a bulge at the equator. And as it rolled through that bulge, it cracked the crust. And that's how we get the 90 East Ridge, almost perfectly straight, pointed at the Himalayas. If that didn't happen, how else did that 90 East Ridge get there? Okay, and then the 90 East Ridge. And then, according to nature, perhaps the longest standing puzzle in Earth science is what caused the Northern Hemisphere ice sheets to come and go? Well, the hydroplate can answer that. You know, for an ice age, you just need it to snow more than it melts year after year after year. Okay, and how are you going to get that? Well, you need warmer oceans so you get more precipitation, but you got to have cooler continents so it comes down as snow. Well, the oceans were warmer because of all of that volcanic activity in the Pacific Ocean, and the continents were cooler because they were higher. Plus, there was a lot of volcanic activity, so there's a lot of aerosols in the atmosphere blocking the heat's sun from getting to the Earth, or the sun's heat from getting to the Earth. And so 4 or 5 years of it snowing more than it melts, and maybe 100 times more snow than what we're getting today, and you got the ice age. But how come you don't have glaciers in parts of Alaska or Siberia? Well, it's because the oceans were warm. There could have been a trade stream going there that warmed it up, or it could be lower elevation. But at any rate, it came down as rain, not snow. Okay, and so then as this is happening, over time, the volcanic activity slows down, so the oceans get cooler, so there's less precipitation, less snow, and the atmosphere is clearing up, so there's more heat coming through, and the continents are sinking down and getting warmer. So this, and then so 100 or 200 years of it melting, the ice cap. Okay, and then the inland seas. This is where you need to understand radioactivity, and I don't have time to go into that, but you can read about it at page 387 at creationscience.com, or just take a half hour and listen to Brian Nichols' Origin of Earth's Radioactivity. And you'll understand why there's weak points in the crust, and then that all that pressure underneath is just going to erupt out of there and make the seas. It's just going to explode out, and now you got the inland seas with salt at the bottom of the chamber there underneath the Gulf of Mexico and the Mediterranean Sea. And some of this stuff, well, exploded with such tremendous force that not only did it escape our atmosphere, it escaped our gravitational pull and turned into comets and trans-Neptune objects and asteroids. Why else are there rounded boulders in Comet 67P? When things hit together in space, they're going to have sharp edges. The only way you get rounded edges is if it goes through a fast flow of water before it gets shot up there. And you can look at the theories for origin of comets. This is on page 321 again, and it's under the hydroplate. There's no problem. There's one moderate problem, but everything else is not. And you say, well, if that happened, wouldn't it leave a mark on the moon? It's like, yeah, it did. The near side of the moon has been pounded. That's what all those lava flows are from. It got pounded, and the far side hasn't. I mean, it's been peppered, but it hasn't been pounded like the near side. And then on the near side, you got these mascons. These are high density impacts or areas. And that's on the near side, and hardly any. I don't think there's maybe one on the far side. So that's very different. And that's how you got the Earth's oldest rock on the moon. And that's how you got it from 12 miles under the surface to the moon. That makes perfect sense with the hydroplate theory. And so now this, I can't play the video for copyright and things, but Astro Alexandra, you can go into this and listen to it yourself. It's asteroid samples from Bennu, so it might be from an ocean world. Yeah, and all right, and so what you see is the map of the mid-oceanic ridge. She points to that, and she says that asteroid Bennu's got serpentine in it, and that's formed when water touches the mantle. And that's what she's referring to. And then she says it came from some ancient watery world. And I'm saying, hey, it came from Earth. And if you want to learn more about that, again, Brian Nickel, The Origin of Comets, Asteroids, and TNOs, and you'll understand that a little bit better. And I encourage you to go through all Brian's videos. He's got a great overview. His slides are incredible. He's got the best Grand Canyon video out there if you want to understand what's going on. And the hydroplate theory explains so many things out over so many areas. And I'm really excited about this. On YouTube, there's the Hydroplate Theory University that's just started last month. They just got 2 videos up there. And Pastor Kevin Lee and Bill Wells, they're going through this. They've been around it. They've seen it. And Pastor Lee has orbital physics in his background. And so he knows what they're saying isn't possible with the Big Bang. And he's in correspondence, even right now, with the professor, an astronomy professor, saying, those things, those contact binaries, they can't help. It can't happen by the Big Bang. But if there's atmosphere and stuff slowing it down, it could help. And she agrees. And that you can go into hydroplate.org and listen to his talk. It's right there. It's the building blocks of life and bacteria found on asteroids. And that's the video that's going to destroy the Big Bang. The predictions of the hydroplate are spot on. The predictions of the Big Bangers are just falling apart all the time. And he's been able to talk to the head of the Don Brownlee, saying, hey, if you try to redirect an asteroid, it'll fail. It'll work if it's a solid block, but it'll fail if it's a bunch of boulders, which is what the hydroplate theory would predict. And guess what? It was a bunch of
1 minute left.
All right. So then you've got, check out those things. I mean, especially check out Pastor Kevin Lee. And he also gave a great earthquake talk. And we're also Hydroplate. We just got on TikTok. We got on Facebook. I encourage people to go there. And if you're a scholar, I'd like you to get, Tectonic Globaloney and in the beginning. But if you're a student, you don't want to get through that book. There's Ellen McHenry. She did a summary of it. Or if you just want to listen to her being interviewed, you can go into Real Science Radio and listen to her interview. And also Walt Brown and Brian Nickel have great interviews there. And then there's this book, 20 Reasons to Question Plate Tectonics. Get this book. It's incredible. And then also Fred Williams. He did a talk on that at the Hydroplate conference. It's the problem with plate tectonics, where you can go through this book instead. And so it's however you want to do it. There's a lot of information there. And this is a topic that needs to be addressed. And a theory that's making accurate predictions and it's being validated by NASA discoveries is being ignored. That's a tragedy in our lifetime. And I'm doing whatever I can to get it into the mainstream. And so thank you, Donny, for putting this together. And thank you, Dr. Feldman, for participating.
Brian Lauer, thank you very much for that roughly 22-minute opening statement. Gentlemen, this is more of a debate seminar, which is what we need. It's a big question. It's an important question. And we want a thought-provoking exchange here tonight. And I can tell that's what we're going to get. So that concludes our opening statements of 22 minutes. Gentlemen, Dr. Howard Feldman and Brian Lauer, thank you for the time and work you both put into the construction of those opening statements. We've got plenty of points and arguments now on the table for a rebuttal. And the rebuttal will be a little more fast paced in the opening statement. We got 10 minutes to address quite a bit here. So what we'll do for the audience, I want them to be on the same page. We have a rebuttal period. Then we'll have a short break. I want to give our debaters just a quick refreshment break. I'll go over some announcements and reminders. Then we're jumping into cross exam. So lots to look forward to. Dr. Feldman, I see your screen share. Do you want me to put that up right away for you?
Sure.
Okay, no problem. So I've got that up on the screen.
That's
Feel
not
free
me.
to. Oh, that's Brian. Oh, there we go.
Let me share my screen.
Sure, take your time. Reminder: 10 minutes.
Should I stop sharing mine, Donnie?
Well, actually, I'm not going to
Brian.
share my screen. Yeah, I'm going to share my screen.
What was that, Donnie? Should I stop sharing mine?
Brian, you can keep it at the bottom if
Okay.
you'd like to, and then anytime you need me to put it up on the screen, just let me know.
Okay.
Dr. Feldman, I do see your screen shared again at the bottom. Let me know when you're
I'm ready.
ready to go. Okay, let's put it up on the screen. 10 minutes.
I shared the wrong screen, didn't I? Let me try it again. You'd think I'd be good at this by now.
To the audience, I'm all caught
Okay.
up on your questions and
I'm ready.
challenges. Keep those coming in. Your questions help us to expand even more on these topics.
Okay, so Brian, you covered so much information and so much of it was false that we just need to go through. I only have time to go through a few things. First, you said that the mountain ranges are parallel to the Mid-Atlantic Ridge. No, they're the opposite of that. These lines are not parallel. Here's the line for the Mid-Atlantic Ridge. There's the African mountains. The Rockies diverge wildly. So it's the opposite of what you said. Let's go to, let's see, I had another PowerPoint. Did I lose the screen share, Donnie? Donnie? Donnie, is anybody there?
Howard, sorry, my screen froze on me and when you lost your screen share, but I put it back up for you.
All right.
You're good
So,
to go.
something, Brian, you've said many times is that scientists don't really understand the Congo Canyon and it was formed by rivers during some massive sea level fall. And, there's so much data that says that's not true. And so this is what I mean is that the entire hydroplate model is built on a house of cards and the cards are individually false. So let's go through this. This is the Congo Canyon. It's a very famous canyon. It's been studied very well. It was carved by turbidity currents. Dr. Brown says there's no deep water currents that can carve these canyons. That's false. They've been known for a long time. And so here's the publications from the 1960s and 70s. They all concluded the Congo Canyon, that specific canyon, was eroded by turbidity currents. Turbidity currents are mixtures of sediment and water that flow downhill, kind of like rivers. These are publications from the 80s and 90s that conclude that the Congo Canyon was not formed by rivers, but was formed by turbidity currents. These are publications. These are publications from the 2000s, and they conclude that the Congo Canyon was not formed by rivers, but was formed by turbidity currents. The sedimentology of turbidity currents is very different than the sedimentology of rivers. Any competent geologist can tell the difference. And then here are studies where they actually put equipment down there and they measured the turbidity currents. So everything you've said about the Congo Canyon in all your videos, and I've watched almost all of them, is false. And you're just not looking at the publications that have evidence. This is not about consensus science. This is about data. And then the other thing you're not looking at is the Congo Canyon is just the latest of a whole series of canyons that are now deeply buried. So whatever process you invoke for the Congo Canyon, you have to have it repeated maybe 100 times. And so these are seismic images of other canyon fills that are now below the sediment water surface. And so this one is down maybe 300 meters below. These are down about 3 kilometers below the seafloor. You've got these incredible channels that look identical to the modern Congo, and they're formed by the same processes. And how do we know all this? Because these are really important petroleum reservoirs. And that's how we know about this. And so the model for these is that when sea level goes down, turbidity currents carve the canyons. When sea level goes up, the canyons get filled with sediment, and then they get abandoned and covered with mud. And then this happens maybe 100 times. How does it happen 100 times? You've got 100 cycles of glaciation. And so all these things are tying together. Hydroplate theory explains none of this. And so you keep saying hydroplate theory explains it. It doesn't. It doesn't explain anything here. You showed that wildly inaccurate bowling ball model. Again, if you scale the Earth down to the size of a bowling ball, the Himalayas will be 1,000th of an inch high, and they contribute no extra mass because it's all counterbalanced by the displacement of mantle. So there's no extra mass on the Earth to affect the spin. That's just completely inaccurate. And so what else did you talk about? You talked about the preservation of fossils. Oh, you talked about chalk. So I'm stopping sharing now. So Donnie, am I still going here?
Yep, you're. I've got you full screen, but without the screen share.
So thank you. So you said chalk is made by the fountains of the deep. Chalk is made by fossils. It's entirely composed of coccolith fossils. And so perhaps you could explain to me how coccolith fossils were formed in the fountains of the deep, or between the mantle and the crust. Chalk isn't just crystals of limestone. It's formed of coccoliths. And there's other fossils in there. Almost all limestone is mostly composed of fossils. So it's not explained by anything coming from the fountains of the deep. And in fact, we've got upright coral reefs in many places around the world. So when did those coral reefs grow? There's coral reefs outside of Chicago. There's coral reefs outside of Alberta, and many other places around North America. And I noticed you mentioned all the salt in the Gulf of Mexico. What's the origin of the salt in Brazil and offshore Angola? Where does that salt come from? And how do you explain it? Hydroplate theory explains nothing. Almost all the statements, I shouldn't say that. Most of the statements about geology in Dr. Brown's Hydroplate book are false. And I showed just a few examples of those false statements. I mean, how many false statements does it take before you admit that that's a house of cards? It doesn't work. You know, you can talk about asteroids all you want, but it doesn't even describe what we've known about geology for decades. And so I don't see how that can possibly be true. And so what were some of the other points you touched on? You said the only assumption is water beneath granite. No, you have to have another assumption to form granite. We know that granite was formed by liquids. There's tons of evidence that it was formed by liquid magma, and you're ignoring all that evidence. And so there's a whole lot of assumptions you need to build into your model, which we don't need as geologists. There's no assumptions needed to form granite. We know how granite forms. The processes are well understood. And so there's nothing there. And let me see if there's anything else here. I'm looking at my list. So yeah, let's talk about fossils just briefly. I've got some whale skeletons here. So, you know, you've said many times, you implied it here, you didn't quite say it, that fossils require rapid deposition. That's absolutely false. Some fossils absolutely require rapid deposition, but other fossils are formed slowly. So here's an example of a whale fossil. I'm not sharing anymore, am I? I need to
Brian,
share. Do I have time to share?
Yes, yeah, because you still have 3 minutes.
3 minutes. Okay. I guess I talked too fast.
I gave you an extra 30 seconds because of the loss of screen share earlier. And I'll pause it here as well while you're getting your screen share up to show us those images.
Okay. So you see the whale?
It's still loading and you're good. Yes, there it is.
So here's, this is a creationist myth that you need rapid deposition to form fossils. There are fossils that require rapid deposition, but they're vastly outnumbered by the fossils that do not require rapid deposition. So here's an example. There's the source of this image. This is a whale skeleton on the seafloor. You can look at the finger bones here. They're just slowly being covered by sediment. So this, obviously, this has been all stripped of flesh, and it's just sitting on the seafloor. It doesn't require rapid deposition. You could put a camera down there and wait a few hundred years, and you'd see it be buried and turned into a fossil. And this is a very similar type of preservation. It's in Egypt, where there's some whale fossils. The vast majority of fossils do not require rapid deposition. In fact, we know they're not involved in rapid deposition. For example, there are whale skeletons that are fossilized where there's epibionts like oysters and things that grew. I mean, they're not growing now, they're fossils, but they grew on the whale's bones. So that meant the whale bones had to be exposed to the seafloor long enough for the oysters and sponges and things to grow on top of them. And there's lots and lots of evidence. I mean, this is my topic. There's lots and lots of evidence that the vast majority of fossils actually were buried slowly, not rapidly. It's a myth that you need rapid burial. For some fossils where you have beautifully articulated fish with all the scales in place, yeah, you need rapid burial for that, but those are in the minority. The vast majority of fossils do not require rapid burial. And in fact, when you look at all the evidence, including bioturbation and sedimentology, and old Earth is inescapable, and you're ignoring all of that sedimentary evidence, which we're going to get to when it's time for me to ask you questions. I'm going to ask you questions, show you photos of this, and ask you questions about it. Okay, so I think that's all I want to talk about for rebuttal.
Dr. Howard Feldman, thank you very much for that roughly 10-minute rebuttal. I will reset the timer. Remind the audience that I am all caught up on your questions. Thank you for the engagement so far. And Brian, make sure to I know I unmuted you for you, and you also have 10 minutes. Would you like me to get your screen shared there, Brian?
Yes.
Okay. I have it up. It says rebuttal, and you're good to go. You have 10 minutes starting now.
Okay, well, with the rebuttal, he's been saying that he implies that plate tectonics it's a slam dunk. Everybody agrees with it. But my rebuttal, I'm going to talk about high confidence and low confidence science, how you actually evaluate a theory, and then see what other PhDs are saying. And then, and whoopsie, whoa, where's that? Whoa, where are we at now? Okay, here we go. All right, so Dr. Rob Stadler, he talks about high confidence and low confidence science. High confidence needs to be repeatable, observable, no bias, no assumptions. Is that what we're talking about here tonight? Is it repeatable? Can we put some stuff together and watch another Earth form? No. Is it directly observable? Can we watch another Mariana Trench form? No. Are we avoiding bias? Well, if we do radiometric tests and they're not blind tests, no. Is that how it's done? I don't think so. Are we avoiding assumptions? No. We have uniformitarianism, which is a huge assumption that's arbitrary. And how do you evaluate theories? To explain an unobserved, unrepeatable event scientifically, which is what we're trying to do tonight, we must first assume the conditions existing before that event. From these assumed starting conditions, we will then try to determine what should happen according to the laws of physics. First, if from these starting conditions we can explain all relevant observations better than any other proposed explanation, confidence in our explanation increases. Okay, and if a few assumptions allow us to explain many things, then confidence in the explanation will be great. And need I remind you, the hydroplate theory is based on one assumption. Okay, how it got there is not part of the theory, but you get the starting conditions and then one assumption. It all makes sense. Conversely, if we need to make many assumptions to explain a few observations, if we need to make many assumptions to explain a few observations, or if new observations cause us to modify our proposed theory, then we should have little confidence in it. Legitimate theory allows us to predict unusual things we should see if we looked in the right places. Verified predictions greatly increase our confidence in an explanation. Published predictions are the most important test of any scientific theory. So I encourage everybody to go into creationscience.com and go to page 447 to 449 and look at the predictions. 59 of them and 10 of them have been confirmed. Or you can go into hydroplate.org and go into predictions. And Fred McNabb says, no, I think there's 20 some that have been confirmed, and he documents them there. So then get all the information and think for yourself and compare it to the plate tectonics predictions. And then compare them head to head. Who can explain trenches, earthquakes, and the ring of fire better? Hydroplate is no problem all the way down. Plate tectonics has serious problems all the way down. And you can go to page 175 and see what Walt Brown's talking about there. And Bob Enyart wanted to make this an interactive part of the website so that it can be adjusted as new information comes out. You can also go into NCGT Journal, which is a voice for new research in global tectonics. And you can listen to an interview by rsr.org, Plate Tectonics. Subduction doesn't happen. And you can scroll down and see a list of geologists who reject plate tectonics. This is not a slam dunk like it's being implied. And you notice that one of them is anonymous. He's afraid to put his name out there because he'll get fired. Another one is N. Christian Smoot, who was mapping the ocean during this time when ocean floors were largely unexplored in 1957, between 1957 and 1970, when the plate tectonics theory was developed. But N. Christian Smoot, an evolutionist, spent 32 years precisely mapping the ocean floor, but it was classified information, so he couldn't release it. But now his book, Tectonic Globaloney, describes the discoveries on the ocean floor that falsify plate tectonics. And you can also go in and listen to Plate Tectonics, Subduction Doesn't Happen. And this is from Howard Meyerhoff, and he was the administrative secretary at the American Association for the Advancement of Science, and he was also an editor-in-chief at Science. And this is what he wrote back in 1972 when plate tectonics was just gaining steam. He wrote, geological and geophysical data from the ocean basins and the continents are now sufficiently abundant to demonstrate that all proposed models for the new global tectonics are seriously in error. And then in 1999, this one writes, in Science Direct, superficially, the mantle plume explanation seems attractive and has had a tremendous appeal. However, its numerous built-in fallacies, contradictions, and failings are unfortunately the little discussed in much of the current literature, and it has acquired the status of an unchallengeable dogma. And there's a lot of unchallengeable dogmas in science and society. Okay, and you can go into that and scroll down and, Warren Hamilton. Let's see what he has to say. Because in 1989, he was awarded the Penrose Medal. And again, that's like winning the Nobel Prize in geology. And he believed in plate tectonics, but came to realize that a generally accepted component of the theory, mantle plumes, is wrong. So in 2002, he wrote this essay, and he says, the different rules of evidence apply to conventional wisdom. Evaluation is not necessary. But if you want to challenge the conventional wisdom, proof must be overwhelming before a discussion is even warranted. I'm seeing that happen today. Appalling papers in support of plumes are now being published in major journals. Suppression of dissent is common. I know of many recent examples wherein prominent members of the dominant pro-plume community have stifled anti-plume reports and research. Although such perpetrators might tell themselves that they are maintaining professional standards, bad science is to them anything contrary to their own conjectures. Widely accepted assumptions regarding the composition, evolution, and behavior of the mantle appear to be in error, yet evaluation of alternatives is actively discouraged. Basic assumptions, often so entrenched that practitioners are unaware that there might be little or no evidence behind them. Adaptation to incompatible data is made by increasing complexity of assumptions rather than by seeking alternatives. Nowadays, much nowadays written under the banner of plate tectonics is deduced from false premises. Modelers of convection are unaware of elementary plate tectonics and do not realize they provide no explanation for plate motions. Science advances primarily when many of us are proven wrong. Breakthroughs, by definition, surprise most of us. And there's a lot of breakthroughs coming. There's a whole bunch. And now keep in mind, this is written by a Penrose winner. And he's saying that there could be no evidence for what they're claiming for how it works. And this is 2018 subduction. It says subduction is a major process of plate tectonics. However, its initiation is not understood. And this is in 2019, same thing. Subduction is incompatible with Earth's surface geometry and geomorphology. It says the geometric shapes do not correspond with the expectations of plate tectonic theory. There is an irresolvable contradiction in plate tectonic subduction theory. And I don't see that in the textbooks. There's a big argument against it, but it can't get in the textbooks because the people who control the textbooks control the funding. But anyhow, this is in 2020. It says, 50 years when I started the first article in 1972. Well, guess what? Nothing's changed. 50 years after the foundational works establishing the geometrics, kinematics, and mechanics of plate tectonics, we still lack a consensus understanding of how plate tectonic systems initiate. And he says, despite considerable theoretical effort, We are unable to directly connect the parameters of these models to the laboratory-derived or microphysical properties of rocks, and instead must tune the model parameters to match observations of Earth's plates. So they have to tune the model to make it work. That should lower our confidence in there. Okay, and then in 2021, it says that the formation and preservation of cratons, the oldest parts of the continents, comprising over 60% of the continental landmass, remains an enduring problem. So there's a lot of problems with plate tectonics. It's not a slam dunk like it's being implied, and I think people should see both sides of this. And I ask people to avoid the tendency to look for someone to tell you what to think. Instead, question everything yourself, starting with this book. And thank God it's available. So if we want to increase confidence in a theory, the starting conditions have to explain the observations using the laws of physics, and I think the Hydroplate does that well. And then one assumption explains many features. You know, that the Hydroplate does that really well, and then it makes accurate predictions. And so then go through and then compare this with plate tectonics, and then think for yourself. And then it's all available. This is so neat because in the beginning, it is available now at Real Science Radio's bookstore. It's on at Amazon. You can get it. And it is such a phenomenal book. It's, let's see here. Let me show you how much it is. I think I moved the wrong one up here. Right here it is. The new books right now are $89. That's the 9th edition. The 7th edition is $125. And the 8th edition is $180. That's a sign of a good theory when it goes up in value. I had a college textbook sometime. I've spent $210 or $215 on 2 of them. And I wanted to sell them back at the end of this quarter or the semester. They'd give me $10 for one and wouldn't take any money for the other one. So that's a textbook. This is a theory that has withstood the test of time. And all I'm asking you is just go into the decision trees, get all the information, and then think for yourself and come to your own conclusion and understand there's dogmas out there that are being funded and carefully guarded dogmas. And if the people object to it, they don't get published. And so that's the other part of the game. And then let's see, what else did we do? How much time do I got there, Donnie?
Brian, good question.
I'm done.
You got about 20 seconds if you want to wrap up.
Okay, yeah, real quickly. You mentioned earthquakes. I encourage people to go into Hydroplate Conference on YouTube. Pastor Kevin Lee did an excellent talk on earthquakes and how it's all going in to fill in the gap in the Pacific. These are the magnetic anomalies that he brought up, the magnetic ridges. And they show this nice, you see how it's nice and perfect in this example, but you go on the other side of Iceland, it's more of a mess. And so that the magnetic fields could be cherry picked. And then these are the predictions also. And there's, also going to page 186, and Walt Brown has about 17 things on how plate tectonics or subduction don't work. And if you don't have subduction, you don't have plate tectonics.
Okay, Brian, thank you for that rebuttal. And gentlemen, we're moving along smoothly. That concludes opening statements of 22 minutes and rebuttals of roughly 10. We have a lot on the table now to engage in everybody's favorite part of these formal debates, the cross-examination, where we get to hold each other's feet to the fire, make each other sweat a little bit, all in good fun, of course. But before we do jump into our cross-exam, I want to give you gentlemen the opportunity to have a quick 2-minute break, restroom break if you need to, fill up your water. And okay, take your time. I'll go over some announcements. So for those that enjoy debates and discussions on all kinds of topics, I hope you're enjoying tonight as much as I am, the Proper Perspective of Geology, Plate Tectonics, or Hydroplate. Dr. Howard Feldman and Brian Lauer. Get those questions and challenges in there. I do my best to give you a little bit on everything. Not only origins, but also theology, eschatology, soteriology, but focusing on origins debates. We've already had several major debates on creation versus evolution related topics this year. And so I'll give a shout out to some of those past debates for you guys to check out. It's been a great year already, 2026 to remember, that is for sure. So this year we had Dr. Peter Line and Gutsick Gibbon, 2 very knowledgeable individuals on the topic of human evolution and hominins. They engaged the question, does the hominin fossil record support creation or evolution? This one was a marathon. Literally, we went for nearly 5 hours on this debate. So if you want to see a good debate with a good representations of both sides of the equation, please do check that out. We had another epic debate here. This one was technical. It was one of a kind, put it that way. This one had Paul Price and Dr. Zach B. Hancock debating the question, are mutational effects a problem for evolution? Essentially, the debate was on genetic entropy. And boy, was it a debate to remember. So please do check that one out. Sam, my award-winning co-host, and I had the privilege of debating Dr. Ron Garrett, former NASA scientist. I always enjoy engaging Dr. Ron. And First Amender, we debated just a couple of weeks ago on Modern Day Debate. The question, does genetics support creation or evolution? I also debated last month, Jackson Rowe, on human evolution. We got to focus on genetics and also the hominin fossil record. Brian Lauer also engaged Jackson Rowe on the topic of the Grand Canyon going back a month or two ago. And so it's been a good year of debates and a good year for debates on creation versus evolution related topics. Okay, break time is over. Dr. Howard Feldman and Brian Lauer, we are ready to jump into our cross-examination. So how we have this formatted is it's a total of 40 minutes. And I've got it broken up into two 20-minute sections. So you both get the opportunity to lead the way in picking topics and asking questions for 20 minutes. What I'd personally like to see, especially because we just had roughly 32 minutes each of presentations and uninterrupted time to present and rebut, is asking direct questions, doing our best to provide direct answers, and that way we can get through as much as possible. Brian just ended with his rebuttal. Therefore, Dr. Feldman, let's give you the first 20 minutes to lead the way. And let's hand it to you. I'll start the timer on your first point or question.
Okay, I'm going to share my screen again.
No problem. Anytime you gentlemen want to screen share throughout the cross exam, I work for you guys. So you just let me know. Say, Donnie, put my screen up, and I'll do so. And Howard, I see it's loading. There we go. It's up on the screen.
All right. So first, I'm going to point out that in your rebuttal, you didn't actually rebut any of the data I presented. I didn't present dogma. I presented data. I presented a prediction about the distribution of earthquakes, which was true. A prediction the Atlantic is getting wider, which is true. A prediction there'd be magnetic stripes in the mid-Atlantic ridge, which is true. And so that was all. Those are all predictions. Those were all data. So let's go into this. I presented the salt on either side of the Atlantic. This is the only place in the world where you have major salts that are adjacent to a large ocean. What's the hydroplate explanation for the origin of this salt? And I'll remind you that the salt on the Africa side is 14,000 cubic kilometers. I couldn't find the volume on the South America side.
The salt, I would say, is from it's from the fountains of the Great Deep.
Why is it only here and no place else in the world? There's no other place in the world where you have salt adjacent to a mid-ocean ridge.
Let me check. I've got a salt map myself. Let me just verify what you're saying is true. That's not true. We've got the if you want to play my slide, Donnie, this is where the salt is. If you want to play mine, you've got salt in the Gulf of Mexico. You've got salt in the Arctic Ocean. You've got salt in England. You've got salt. Let's see. You've got salt.
Well, there's a lot of salt. Wait, that's not what I'm asking. There's a lot of salt that is on continental crust. That's true. The salt in the Arctic, that's on continental crust. There's lots of salt basins scattered around the continents. The Gulf of Mexico is not adjacent to a mid-ocean ridge. It's an enclosed, semi-enclosed basin. This map is missing the salt that I'm showing here. And so I'm asking you, why is this the only place in the world, if you could share my screen again, why is this the only place in the world where you have salt adjacent to a mid-ocean ridge? There's no other place where this happens.
Where that's adjacent to a mid-oceanic ridge?
Well, it's on either side.
The mid-oceanic ridge is hundreds of miles away from each one of them.
Okay, so you explain it. How did it get there?
Well, I would say it's salt from the subterranean water chambers, and it maybe just gushed out at that time when that part of the water is
and
shooting out. Maybe
it just happens that when you bring the continents together, it matches up perfectly. That's just a coincidence.
Yeah, that's just a coincidence.
And so when did the salt occur? Because you've got several kilometers of sediment below it, several kilometers of sediment above it. So what was the series of events that went from sedimentation, salt, back to sedimentation?
Well, it could be what was coming out of the mid-oceanic ridges at that time. At one time, it could be the limestone coming out.
So why
time,
wasn't
it could be the salt coming out?
Why isn't there salt?
And then the sediment. Well, let me answer, please. And then the sediment that's on top of it probably got eroded off the continents as the floodwaters were receding off the continents.
Yep. But this is the only place where this occurs adjacent. I mean, on either side, symmetrically on either side. You don't see it in the Pacific. You don't see it anywhere in the Indian Ocean. Only here. And so
so you're saying that was together. So if I understand you right, you're saying that those continents were together, and there was this narrow ocean that dried up a lot. Okay. Okay,
correct.
Well, if it dried up, if it evaporated when the next ocean came in, wouldn't it just absorb it again? Or how does that work? I mean, how thick are those salt layers?
Well, they range because they've been deformed, they range up to a couple kilometers thick.
A couple kilometers thick. Do you know how much salt water has to evaporate to get a couple kilometers?
Huge amount. So we're
what's the ratio? Well, it's 60. It's 60 times higher. You have to have 60 kilometers of water evaporate to get 1 kilometer of water.
Yeah. So the idea is that there's water constantly flowing into this narrow basin. It's evaporating. The crystals are falling to the seafloor. So it does take millions of years for sure. You can't do it quickly.
Well, that's the uniformitarian assumption.
Well,
and I would suggest that it could happen in a global flood with the subterranean water chambers.
Well, then why didn't we get it everywhere? Why only here?
Well, like I said, it depends on what's being shot out of the subterranean chambers at that time.
Yeah, I mean, I think this model makes a lot more sense, and it's consistent with the sedimentary deposits. So you said chalk is made by the fountains of the deep. Chalk is made almost entirely of fossils. It's probably 99% fossils. So what fossils came from the fountains of the deep to make chalk?
Yeah, then maybe that word probably shouldn't have been in the slide. Okay, that's a slide that I'd learned, and I'll just take chalk out of there. We'll put limestone. Thank you for.
Well, what kind of limestone isn't made of fossils? Almost every limestone I know is made of fossils.
Oh, you got those blooms, those limestone blooms in the Bahamas. When the conditions are right, limestone precipitates out of water.
Not really. So let's look at some limestone. So this is there's a picture of cross-bedded Salem limestone in Indiana. This is all fossils. Everything in here you see is a fossil. So when did this cross-bedding occur? Was it before or after the fountains of the deep?
Well, I would suggest it was after the fountains of the great deep.
Well, but it was covered by the time this has been eroded down. So there's another mile of sediment that's been removed. When was that mile of sediment deposited?
During the fountains of the great deep.
Well, then how did the cross-bedding form after that?
Well, that could have been when they were. Well, the cross-bedding has to do with the how fast the water is going when the sediment is laid down. So when that layer was being laid down, the water was moving fast. And then as the flood goes on, it lays down more sediment, and then it doesn't disturb this.
And where did all this sediment come from? Because this is all fossils.
Well, like I said, it came from the. What do you mean?
This is 100%.
I see. I understand the question. Those are fossils in there. What kind of fossils are they?
Well, I have a close-up. So here's, I'm going to actually put this on display mode so here's a quarry. I did a lot of work in the Salem limestone. This is the Salem limestone where they cut it for building stone. So, and this is a thin section looking at the Salem limestone. There's 1 millimeter. Everything you see in here is a fossil. So this is a crinoid. This is a snail. Almost everything here is a crinoid. That's a foram. So what's the source of this? This is, I don't know, what's that, 100 feet thick? How do you get 100 feet thick accumulation of fossils at this time? When did the organisms grow? When did they accumulate?
Well, I would
And
say
this is the same composition of the limestone that's cross-bedded. And so I don't understand how that can happen. And then whoops. So here's another quarry in the Salem limestone. This is a cemented bit of limestone. This is the same composition of this on either side. It's just a little darker here. And then you've got a coral growing here that's absolutely in place. It's growing on this little ledge of limestone. And this is the same quarry. That limestone's actually bored. So we knew it was cemented before this next unit was deposited. So when did this coral grow?
Well, the creatures were living before the flood, and then they got buried in limestone, and then it got cemented together.
But this coral is in growth position. That's where it grew. It's still attached to the ledge.
Well, then it got buried there. It got
Okay,
buried
but then
there.
what about the several hundred meters of sediment below this? When did that form?
That could have been before the flood too, I guess. I'm not sure exactly where you're talking about, and maybe this was. Yeah, I guess I'd have to look into that a little closer.
Well,
but it makes sense to me that the creatures before the flood got buried in limestone, since limestone was coming out of the fountains of the Great Deep.
Which part of this limestone was coming out of the fountains of the Great Deep? Was it the crinoids or the forams?
No, it would be the stuff that's in between them, the stuff that's cementing them together.
Well,
all over the world, you've got sedimentary rock that's evenly cemented, and that came from the limestone.
Yeah, but this rock was cemented before that coral grew. So if this is before the fountains of the deep, when did this get cemented?
Yeah, I guess I'd have to look at that. That's your interpretation of it. There's other interpretation, and I've never seen that before. So
it's
hard
for
me to comment on something I haven't seen.
This is called a hard ground in limestone. They're extremely common. There's a lot of hard grounds in the Salem limestone. So if you look at this, I couldn't find the photograph, but I have a photograph of that boundary, and the cement is actually truncated. So you can prove that the cementation happened, then the coral grew, and then more limestone was deposited on top of it. And nearly all this limestone is fossils. And so I don't think you can fit this into a fountains of the deep timeline. And so let's look at another example. These are limestones from the Silurian now, also in Indiana. So here's a crinoid stem, and then that's a coral. Everything you see that's light colored here is algae. All the dark colored stuff here is bryozoan. So when did this grow? So this is in the layer below the Salem limestone, actually several layers down. And so you have the same timeline problem here of when did all this grow? These corals were in place when we plucked them out of the outcrop.
Well, I would suggest that the coral and the algae were before the fountains of the Great Deep, because do you see algae fossilizing today? And I would submit that the limestone came from the fountains of the Great Deep, and they buried them, and then there's sediment on top of it from the fountains of the Great Deep.
But the limestone's this is all fossil. Everything you see here in this limestone's a fossil. So none of it came, and you've got, if you're going to say this is before the fountains of the deep, you're going to end up with kilometers of sediment that are before the fountains of the deep, because we see these kinds of features in almost every layer.
You say everything I see is a fossil?
In this diagram, absolutely. In this cross-section, everything you see here is a fossil.
So what's holding it together?
The fossils. I mean, this coral is attached to that crinoid stem. This algae bit is attached to that coral. This bryozoan is attached to the algae.
And I would say that the limestone covered it, and it turned into fossils.
This is actually covered with shale, but
shale covered it.
Okay,
something had to cover it.
But the limestone that covered it is this, and you said this is also before the fountains of the deep.
Okay, maybe I should have said I have to look at it to see. I have to look.
But this is all very common, and so what I'm saying is virtually all limestone is made mostly of fossils, and fossils didn't come from the fossil fountains of the deep.
Well, when limestone is formed, it releases a molecule of carbon dioxide. There's 60,000 times more carbon dioxide molecules than limestone molecules. And so you're saying that they just vanished somehow, that didn't happen?
No, I'm saying you need to read these papers. These papers deal with that topic exactly, and they account for the release of carbon dioxide. And so all of this has been accounted for, but you're just unwilling to look at the literature that accounts for it. And
well, maybe tell us what the literature says. Where did the 60,000 more
well,
times
it was released over millions of years, and so it wasn't released all at once.
So where did
and
it didn't go, and it just vanished?
No, it didn't vanish. It became part of the atmosphere. So there's no loss of mass or loss of volume. But the thing is that these corals that we see upright growing in the limestone are very common, and they're unaccounted for in your model. There's no evidence of liquefaction. There's if you say that wherever you see corals growing in place, that was before the fountains of the deep, you're not going to have any sediment left. Everything will be before the fountains of the deep.
Okay, well then it won't make such blanket statements that everything.
Well, but you have many times.
But there's probably exceptions to everything that's
well,
out
it's not
there.
exceptions.
So I'll be more careful on what I say.
This isn't the exception. This is the rule. This is what's most common. Is what you're saying is an exception. You're just unaware of it because you're not willing to read the literature, I think. So okay, so let's go on to. I want to show some other slides here. So these are trace fossils. This is a dung beetle burrow from an outcrop in Spain with the dung ball in it. This is a dung beetle burrow, and we're doing this by analogy with the morphology of modern dung beetle burrows. There's the dung ball at the base. Do you think any of this, when would these burrows have been made relative to the fountains of the deep?
Maybe they were made during I guess I shouldn't comment on it. I don't know. I've never seen this. I don't know what you're talking about and where it is, but maybe it happened during the flood, because I don't see dung beetle tunnels being fossilized today. So I think something special happened in the past.
How do you know
caused it to fossilize?
How do you know they're not being fossilized today?
I don't know. Well, show me where. Show me where they are.
Well, there's lots of fossils that are forming today.
Well, dung beetle. Show me a dung beetle fossil.
Well, there are dung beetle burrows that are getting buried by sediment, and you have to wait a long time. Sandstone takes a long time to fossilize, to turn into rock. But there are you've said fossils aren't forming today. That's absolutely false. Fossils are forming today, and in large numbers. You can observe them in the Bahamas. There's limestone being created that is packed with shells. A shell in limestone, that's a fossil. Some of the limestone that's being created includes things like Coke bottles incorporated into the limestone, so we know it's modern. So your statements that you've made many times that fossils are not forming today are false, and they're false by a wide margin. I'm saying worldwide fossils being buried are not forming today. The limestone is what's precipitating out of the ocean that's covering up the Coke bottles. I'm saying this, and Ron Neller, he's a fluvial geomorphologist. He says there's not enough sediment coming down to fossilize stuff in the worldwide layer. I mean, so I'll just leave. Well, that's absolutely not true. I mean, it's just not true. So
Ron Neller, who's got the PhD in geomorphology, says it is true. So people can listen to Dr. Feldman, and they can listen to Dr. Ron Neller, and then they can decide which one they want to believe.
So these are marine burrows in a sandstone. Marine burrows can't form unless the organisms have access to oxygen. You need to have a stable seafloor, and they need more or less clear water. They don't form in turbid water. So when did burrowed limestone is very common, or burrowed sandstone rather is very common. So when did this get burrowed?
I would suggest during the flood. They got buried and they tried to get up to more air, and they kept going until they ran out of air.
These are feeding burrows. These are not escape burrows.
They're what burrows?
Feeding burrows. These are feeding. They're not escape burrows.
Well, how do you know that?
By analogy with modern organisms, we can watch the burrows form, and we know the morphology.
Well, is it possible there was an animal that went extinct that could have made these?
Unlikely. We find these same kinds of burrows being made today, so we know what organisms like these are shrimp burrows.
And again, so that's what made the fossil? Do we see these burrows being turned into fossils today?
we see anything that forms in limestone, we see being made into a fossil today, absolutely, in large numbers. That's easy.
These burrows, do you see these burrows being formed today?
Yeah, they're being formed today in the seafloor and then being slowly buried. And so, how deeply do they have to be buried before you call it a fossil? You tell me.
I'd say it has to be like a rock.
Or 1,000 feet down or a mile down. How far down do you want? However far down you want, I can show you features that far down.
It has nothing to do with depths. It has to do with, is it a rock? Basically, in layman's term, is it a rock or is it sand? If it's a rock, then it's a fossil.
Okay, so let's look at this slide then. These are modern current ripples that are on a tidal flat in France. These are fossil current ripples in the Devonian. This is a cross section of a current ripple in Texas at a place where I trenched it, and then these are fossil current ripples. This is rock that is 1.9 kilometers below the surface of Wyoming. And then these are current ripples from a reservoir in Nigeria. This is 2.6 kilometers below the seafloor. It's loose sediment. It's just loose sediment. It's not rock. So, when we look at the modern seafloor, what we see is a very gradual transition from sediment to rock. And that transition is several kilometers below the seafloor. So, and there are burrows. I didn't happen to pick a piece of core that has burrows in it, but there are burrows in here that look just like the burrows forming today. So, I mean, how would you call the burrows? And I should have gotten a slide that had some burrows in it, but they're in our publication. So burrows in soft sediment that are buried 2.6 kilometers below the seafloor, do those count as fossils or not?
Well, are you telling me that these are permineralized? Are these hard as rock? Or are they?
No, this is loose sand. This is loose sand.
This is just sand. How did they preserve that shape?
What do you mean?
Just sand is just going to go flat. How did it preserve this shape?
That's not true. That's what I'm saying. It's not true. This is a petroleum core. And the reason I could show you this, there's a lot of stuff I worked on that I can't show you, obviously. But the reason I can show you this is because we published it. I should have put the full citation here. That's my fault.
Howard, I would say you have time for one, maybe two more questions. Gentlemen, since we have 30 seconds left, let's do two direct questions, two direct answers.
So you claim that most of the sediment is deposited by liquefaction. How do you get current ripples at 2.6 kilometers below the seafloor with liquefaction? I
didn't say liquefaction once tonight.
You didn't, but you said it in the past. That's for sure. So this is loose sediment, and every place we have cored sand going all the way down kilometers below the seafloor, the sand or sandstone is either cross-bedded, current rippled, or burrowed. There's no indication of particularly rapid deposition, and there's no indication that conditions were any different than what we see going on at the surface today. So why don't we see anything different?
Okay, let's do this, gentlemen, since we are a little bit over. Brian, please respond to his question directly and quickly, and then we'll shift to our next cross-exam.
Yeah, I think there's a lot of assumptions in that question and the cross-bedding, and it could have happened when it's compressing too. As those things are moving, they can cross-bed as they're moving also. And as far as them being preserved, they had to have something, but whatever. We'll just leave it at that.
Okay, gentlemen, very good. Hopefully the audience, there's been some good engagement. That was so good that I was even getting involved in the live chat. So hopefully this all sparks some good questions from the live chat in order that we can expand even more on what has just been discussed for the last 20 minutes. I thought that was really good. Some good points, some good back and forth for sure. Okay. The next 20 minutes will now feature Brian leading the way in cross-exam. So Brian, whenever you're ready, I've reset the timer and I'll start it again on your first question. Go ahead.
Okay. What are the current published predictions of plate tectonics?
Well, I reviewed a whole bunch of predictions. I don't know what the
current ones. The current ones. What do they expect to find that they haven't discovered yet?
I don't know the answer to that.
Okay, and then you gave me a couple of confirmed ones. How thick are the?
More than a couple.
How thick are the plates? How thick are the plates?
Oh, that depends. So oceanic crust, the oceanic crust is about 6 kilometers thick, and then there's lithosphere below that. That's another 20 or 30 kilometers.
Okay, and how many plates are there?
I haven't counted. I don't know.
Okay, Donnie, can you share my screen? Okay, they've got, according to there's 7 major plates, 15 minor plates, and 1,200 micro plates.
That
So what
sounds about
force and
right.
mechanism breaks the crust into 1,200 plates?
Okay, what's the question?
What force and mechanism breaks the crust into 1,200 plates?
Oh, mantle convection.
Mantle convection. Okay, how does subduction begin?
There are some models on how it begins, but it's not clear. Now, there's a
Okay.
huge problem that with creationism.
Well, just do you have an answer on how it begins, not how it what they're talking about? Just give us the answer or not.
Yeah, there's I can give you some citations of how it begins.
Okay, well, in 2021, they said they didn't know how. And how does a plate get pushed or pulled without crushing or cracking the plate as it's being subducted?
It's both the density of the plate because it's denser than the mantle, and it's convection in the mantle that's pulling it.
Okay, interesting. Because they remember the Hamilton said that the convection people, they can't move the plates. Okay,
That's
why
not
are
true.
divergent areas almost 3 times more than convergent areas? Why are they
Because
spreading?
convergence happens at a more rapid rate. If you actually add up all the rates of the motion, they sum to 0.
But so you're squeezing the plates into a smaller area.
No,
It's like
no,
having a
it's the-
conveyor
the-
belt that's 6 miles wide going into an exit, or on the other side going into 3 miles wide.
No. If
Okay,
you
how
look
do
at,
plate
if you look at, let
tectonics,
me
how
answer
do
the
plates
question,
reverse
Brian.
direction?
Let me answer the question. You asked me a direct question. Let me answer it. Go back to the.
You did
previous
answer
slide.
it, and then I commented on it.
If you look at you don't have the rates in there. If you look at the rates, although there's a lot more spreading centers than there are subduction zones, the rates of creation at the spreading centers are slower, and the rates of subduction are faster. So if you integrate it over the length, the same amount of crust is being subducted as being created. So there's no
right, and that's what I said. It's like having a 6-foot conveyor belt going into a 3-foot exit.
No, that's absolutely not true.
Okay, we'll agree to disagree. How do plates reverse direction?
What plates of reverse direction?
They can measure it. It's on page 182 at creationscience.com.
And what's the citation for this?
We'd have to look. It's number 17.
Well,
okay, we'll move on. How did the Mariana Trench form?
Subduction.
Okay, so subduction. Why are most of the trenches in the Western Pacific and not everywhere else?
Because the Atlantic Ocean was formed as the continents separated, so there's no subduction in the Atlantic, and so you have to, if you expand the crust in one area, you have to contract it in another, and so that's where the subduction started happening.
Okay, so that's being subducted. So why are there mass deficiencies at trenches? If things are going down there, so there should be more mass, but there's less mass.
What do you mean by there's less mass?
There's less gravitational pull. You weigh less over a trench, and there's less gravity.
Well, that's because it depends. You have to look. Are you talking about free air gravity maps or Bouguer gravity maps?
Okay,
which one
we'll move
are you
on.
referring
Okay,
to?
how do the trenches form in an arc and cusp shape?
There's actually a paper about that if you start with just the basic physical constraints of the plates and you let subduction run, you end up with arcs.
I'd like to see that one. Okay.
Yeah.
Where's all the sediment that's scraped off of the subduction areas?
I'd like to share my screen to show that.
No problem. As you're doing that, just to fill dead air to the audience, I see a lot of engagement, debate, commentary. If you could take your arguments in the live chat, formulate them into questions so I can actually utilize them in the Q&A period to make this even more comprehensive. And boom,
let's just skip this one. Okay, why doesn't the Atlantic floor have similar texture as the mid-Atlantic ridge from which it came?
I'm ready
to I'm just gonna jump in real quick. I have the timer pause anyway, so you're not losing out on minutes, Brian. If you could, that previous question, Brian, can you reiterate it? Dr.
Where's the
Feldman will give
sediment
you a
that's
quick
scraped
response.
off at the subduction zones? Where's the volcanoes and the table mounts? Where's all that stuff that got scraped off as the plates are subducting?
Here it is, right here. So here's an example. This is from offshore Japan. Most subduction zones have a thick wedge of sediment called an accretionary prism of all the sediment that has been scraped off. And so here you have a subducting plate here. That's oceanic crust. And then this is the seismic, and it shows, you can see here, all that seismic is all distorted and it's all compressed. And so there is in this location 2, 4, almost 6 kilometer thick succession of sediment that has been scraped off. And what I've done is I've taken, this is the seismic line from the paper, and I've projected it at an angle.
Okay,
so
thank you. Okay, thank you.
seafloor.
You've answered the question. Let's move on. But on
All
page
right, but you
22.
see this a lot. You see this a lot in a lot of
thank
different
you.
trenches.
Okay, well, it should be as high as Mount Everest if it's been going for
Nope,
millions of
nope.
years.
Who says it's? I don't.
That's
I'd
the
like to
20
see that
reasons to
calculation.
question Mount Plate tectonics.
Brian,
All
do you want
right,
your screen up again?
Yeah, I do.
Go ahead.
All right. Why are rocks of the St. Peter and Paul there? That's in the middle of it's right on. That's where the mid-Atlantic ridge pops up. There should be 10 million years old. Why do they date that 2 billion years old? If the mid-oceanic ridge is where the new stuff is forming, how come stuff is dated so old?
Well, I'm not familiar with that paper, but
okay.
I can't.
All right,
I
that's
can't
from
answer that.
Melson.
I'd have to read the paper, but
okay, yeah.
I look at it from 1972.
Okay.
Who knows what errors there were.
Have you dated rocks before?
Have I personally dated rocks?
Yes.
No.
Okay. All right. Why is there supercritical water under the Atlantic Ocean?
Where?
It's 5 degrees just south of the Atlantic equator near the southern end of the mid-Atlantic ridge. Supercritical water's coming out of there. How did it get down there?
Well, the mid-Atlantic ridge is spewing basalt, and so any water that sinks down into the plate is going to be heated by the basalt.
Yeah, and then it's going to turn to steam. It has to be under pressure to turn into supercritical water. It's got to be under 3,200 psi to become supercritical.
Well, I'm what's the source of that quotation?
New Scientist, Catherine Barrick, 2008.
Yeah, I'd have to look at it, but
okay, all right.
You've got a lot of heat down there.
And then but you need to have it be pressurized. Okay, so again, you got 1 molecule of limestone to make 1 molecule of CO2, and you got 60,000 times more molecules of limestone than you do of carbon dioxide molecules in the atmosphere. You said it went into the atmosphere, but it's got to go somewhere. And some of it gets into the plants and the coals and the ocean. I understand that. And that adds up to 42,000 or 44,000. But that's still 1,000 times more limestone particles than carbon in the limestone than in all other sources combined. Why is that?
Well, I started looking at these numbers. The amount of coal and oil is inaccurate. It's way more than that. And so, if you look at the amount of CO2, I mean, this is integrated over a 4 billion year history. And so it's released gradually over time. So I don't see where the problem is. And this
so you're saying that there's 1,000 times more coal and oil than what Walt has here?
There's like 10 times more. Yeah.
10 times. So it's got to be 1,000 times more.
Well, I don't know. I don't know why that's.
How did the Bahama Bank form? That's limestone deposits 250 miles by 800 miles, and that's 6 miles deep.
Well, as the limestone forms and it accumulates to the surface, there's isostatic adjustment, and then more limestone, isostatic adjustment, more limestone, isostatic adjustment.
So it just happened to grow at the perfect rate for 6 miles. Is that what you're saying?
Well, if it didn't grow at the perfect rate, we wouldn't have the Bahamas. There are other islands like off there.
I would disagree. I would say that it precipitated out. Where's the world's largest underground salt mine?
Brian, let's go back. It's almost all fossils. It can't have precipitated out. You're ignoring that probably 90% of the mass of that limestone is fossils.
Okay, well, we'd have to see that. Okay, we'll agree to disagree. Where's the world's largest underground salt mine?
I have no idea.
It's underneath Lake Huron, 1,800 feet under Lake Huron. How did it get there?
That's a really interesting story. So that's what's called the Michigan Basin.
Well, we don't want stories. We want facts. How did it get there?
I'm trying to describe,
Okay.
if you'll let me go.
Okay.
So if you look at the geology of that area and look at the stratigraphy, there's a ring of reefs, of coral reefs around the basin. So it's not really shown very accurately here. Oh, I can't point, unfortunately. But in the Michigan Basin, there's a ring of reefs. If you look at a map view, I don't have a map handy, so I can't show it. But there's a ring of coral reefs around the Michigan Basin, and then the salt is confined to the middle of that. And when you look at the cycles of salt in the Michigan Basin, you see chemically precipitated. It's one of the few places where you actually see chemically precipitated calcite. Then you see gypsum, and then you see halite. And if you evaporate seawater, what do you get? The first thing you get is calcite, then you get gypsum, then you get halite. So you get these cycles of halite with other minerals, and the order of the cycles is exactly the same as what you get from evaporating seawater. So I think.
So how much seawater did they have to evaporate there? Remember, it's got to be 60 times more than what it was.
Yeah,
okay,
yeah.
How do you get salt domes? How do you get salt domes in the Gulf of Mexico? You got 30,000 feet of sediment and over 1,000 feet of salt, and they go up through the softer sediment. Some of them are taller than Mount Everest. How do those form?
Well, salt is less dense than the sediment around it, and so it gradually flows. And this actually can be measured.
That's only if it's liquid salt. If it's liquid sediment.
No, that is absolutely not true. Solid material can flow. Like the mantle is solid, but it can flow from convection. And the same thing with, this isn't convection, of course, but salt can flow. It can be measured in real time. We can observe it happening today. And
so how does convection work for plate tectonics? Are you talking about those plumes that people have disagreed with?
Yeah.
Well, there's the crossover depth that's 200 miles down. Once the magma's there, it gets too dense. It sinks. It can't rise up.
But it's not magma. The plumes are not magma. Nobody's claiming they're magma.
Okay.
The plumes. Right. So what you have to do,
okay.
Let me answer, since you brought this up.
Okay, why did Russia find hot, salty water flowing through crushed granite 6 miles under the Gola Peninsula?
Can I respond, please, that previous
Okay, let's do this, gentlemen. Howard, let's hand it to you. Feel free to respond to the previous question, and then Brian, either follow up on whatever his answer is or move to the next question.
So there's a concept in physics called the Rayleigh number, R-A-Y-L-I-E. It's either I-E-G-H or E-I-G-H. And if the Rayleigh number is over 1,000, if I'm doing this from my memory from distant courses, then a solid object can convect. And so with the mantle, the Rayleigh number is something like 10,000. It's way over the rate at what you need for the mantle to convect. So solid mantle can convect over a very long period of time. In fact, when you look at the
that's good. Can we move on?
Let me finish talking. When you look at the physics of it, it has to convect unless you want a miracle to prevent it. Okay. And so it's completely consistent with physics. So it's not plumes of magma that are being created. It's plumes of hot, solid mantle that is moving very slowly over long periods of time.
So you got solid rock moving up. That's not mantle. Okay.
Yes.
Why did Russia find hot, salty water flowing through crushed granite 6 miles deep under the Kola Peninsula?
Well, first of all, it's not crushed granite. That's
okay. We'll agree to disagree.
Pressure. It's fractured granite, and so there's
fractured.
Yeah, there's no problem. I don't understand what the problem is of finding.
How do you get water that deep underneath the ocean? If the Earth was a molten blob, how do you get water that far down? Because granite's going to seal it off after 5 miles. There aren't going to be any.
I've read that in Walt Brown's book, and that's a complete mystery to me why anybody would think that. There's lots of wells that go down 6 miles, and there's porosity preserved with salt water. This is not unusual.
Okay, how did the 90 East Ridge form?
So there was a hot spot, and as India is moving north, the hot spot stayed stationary. So as India moved north, it left behind a series of volcanoes.
Okay, interesting. Okay, in your talk with Rebecca, you said the point I'm trying to make is there's not just one of these river channels. You have to have sea level going up to form these widespread marine deposits, and sea level going down, and you get the river channels cutting in them. Then sea level goes up, and you have to have this happen in the Cretaceous dozens of times. Is that an accurate statement?
Yes.
Okay, do you stand by that?
Yes.
Okay, so if the sea level's going up and down, wouldn't the high tide and low tide destroy those riverbeds?
No, because there's enough sediment coming in that would that covers them up.
But as it's coming in, you're going to have high tide and low tide twice a day. So that's going to pound on the beach. Eventually, the beach is going to go up, and then the beach is going to come down. Wouldn't that process get rid of those riverbeds?
No, I don't know why you would think that.
Well, I don't see any riverbeds at the when I'm at the beach. I don't see any riverbeds being preserved. Okay.
Well, you have to look at what's below the beach, but there are some of those valley deposits actually have tidal cycles. Tidal cycles in them, and so we can see the record of tides.
How does sea level go up?
Let me answer. That doesn't mean the tidal currents were strong enough to actually erase it.
Well, okay, we'll move on. How does sea level go up?
There's several different reasons. So when we say sea level goes up, what I mean is relative to the land surface. And so you really can't tell if it's water going up or if it's the land going down. And there's several different mechanisms that can cause that. One is glacial cycles. So every time you build up glacial ice, sea level goes down. When the glacial ice melt, sea level goes up. The other way is with tectonics. So the example you were citing before is in what's called a foreland basin. And so there could be stresses in the foreland basin that are causing the land to go up and down. So so
you're saying the land goes up and down, not sea level goes up and down. Is that what you're saying now?
No, I'm saying it can be either.
Either the land goes up. Okay. So it goes up or down. Okay. You're saying that's how it goes up. So then how does it go down?
Well, tectonic forces can go back and forth or sea level can go up and down as glaciers form and then melt. When glaciers form,
okay, so how much would the ocean have to go up to cover that paper that you were talking about, the Iron River field? That was at about, I clocked it at about 1,900 feet.
Well, it's 1,900
So every time
feet
it goes up, it's going to flood the earth that's in green, and then every time it goes down, it's not?
No, because it's at 1,900 feet today. It wasn't at 1,900 feet in the past. That was a foreland basin that was, much of it was below sea level. So there was a vast seaway that connected the Arctic Ocean to the Gulf of Mexico in the Cretaceous. And so what happened is you had forces that were building mountains to the west. And if something goes up, something else has to go down. That was a foreland basin, and that was flooded.
So what's the mechanism? What's the mechanism that causes these continents to go up and down dozens of times to form these riverbeds and marine levels?
Well, I was just describing that there was a thrusting event called the severe orogeny. And so
what caused that? What caused that?
That was caused by a subducting plate at the west coast.
They don't know how subduction begins. How could that happen there?
How
did subduction begin?
I don't know how subduction begins, but that doesn't mean it's not happening. So you asked me a question. I'm trying to explain it. It's not at 1,900 feet. It wasn't at 1,900 feet back then. We've got a record of vast marine deposits that connect the Arctic Ocean to the Gulf of Mexico. They stretch all the way across Canada, south into the U.S. And there was a mountain building event. Whether or not you accept the mechanism is irrelevant, because the mountains did happen. And so that forced the land to go down, and that's how the ocean got created. And then these are the deposits that I'm talking about, were the fill as that trough was filled up.
And that had to happen. And that had to happen dozens of times. Is that right?
Far more than dozens. Yeah.
Far more than dozens. Okay. And this is from the Colorado Grand Canyon website. It says the way in which the uplift of the Colorado Plateau occurred is puzzling. The Rockies were dramatically crushed and deformed during the uplift. The Colorado Plateau rocks weren't altered significantly. Instead, they were just lifted high and flat. Scientists don't know how this uplift happened. Do you?
Nope.
Okay. Well, I would submit that the hydroplate theory explains that very well. Okay. How did the Powder Ridge coal seam form? It's 200 feet thick and it's 60 miles wide by 60 miles.
That's Cretaceous.
When Tim Clary went there, when he was in class, his professor says, he said, we got nothing to explain this much coal over this much area. So what do you have to explain that much coal over that much area?
Well, I haven't. I've been to a lot of outcrops of coal, but I haven't been to that specific outcrop. Although it doesn't look that far from where I live, so I can't address that coal specifically. But I certainly can address lots of other coals that I've seen. Many coals have roots beneath the coal, so that means the plants were living there, and you accumulate plants over time in ultra wet, in what are called ever wet climates, and so you have a mire that accumulates plants and it gets compressed into coal.
You have time for one more question, Brian.
Okay, how did the Ice Age begin, and why did it stop?
Well, there wasn't one ice age. There were dozens or hundreds of ice ages.
And how did they begin?
Well, the common explanation is the Milankovitch cycles of climate, and they work for the last few ice ages, but you go back, I know it gets a little bit tough to explain.
So how come Alaska and Siberia didn't have glaciers?
Yeah, I don't know about the evidence for that.
Well, it's in the textbook.
Well, okay, so there was less snow, less precipitation there than other places. It depends on the climate and the wind, which directions the winds were blowing. But, the evidence that we had multiple generations of glacial cycles. We have the evidence from the sedimentology of shelf edges. We have the evidence from the isotopic ratios in 4M shells and marine sediments, which has been observed worldwide. And so we have all these isotope cycles that the only explanation that's ever been offered for them is multiple cycles of glaciation. And then there's the morphology, geomorphology.
Okay, I got to say, that was an excellent cross exam, 40 to 45 minutes. It flew by. I blinked and it was over. I feel like I could listen to very easily another couple rounds of that from each of you. So very good, fast paced, stimulating, just a good shot for shot cross exam. So clearly you both have put in the necessary amount of work, time, and study to give us a debate to remember on the topic of plate tectonics versus hydroplate. Fantastic job. Okay, I really enjoyed this. We've got closing statements in light of everything discussed so far. Now we get the opportunity to land the plane on our respective positions, leaving no stone unturned and addressing anything we feel has been left hanging, which means to the audience, you have roughly 10 minutes before we begin to engage with your comments. So please, there was a lot discussed there. As the host, I really enjoyed that. It got me thinking about how would I answer those certain questions and challenges. And so I'm sure it got you guys thinking as well. So if we could, let's do our best to formulate some questions based directly on what was discussed over the last 40 minutes so we can expand even more. I'd like to see that. So, okay, 5 minutes each, starting with Dr. Howard Feldman. And okay, you just let me know when you're ready.
Yeah, I'm ready now. I'm not going to share my screen.
Okay.
So hydroplate fails. When you look at Dr. Brown's book, his description of the edges of continents is so wrong that it's not even close. His description of the sedimentology and stratigraphy of sediments is so wrong, it's not even close. It can't explain the formation of limestone because most limestone is filled with fossils, if not completely composed of fossils. And so where did all the fossils come from? It can't explain the existence of coral reefs. Coral reefs are incredibly common, and there's lots of them scattered across North America. When did they grow? And in some places, there's kilometers of sediment beneath the coral reefs, and then kilometers of sediment on top of the coral reefs. Brian brought up salt in the Michigan Basin, and there's a ring of coral reefs around that. How do we know that? They're not exposed. Well, there's a few exposed. Mostly we know it because they're petroleum reservoirs. And so, and we have all sorts of cores that are through that. So we know the cycles of evaporites match the cycles that you would expect from evaporating seawater. And with coals, when you see rooted coals and you see lots and lots of plants preserved in the coals, that is completely consistent with mires or swamps. And, you have to look at the types of plants that are in the coals. For example, in the Pennsylvania, which all the coals in the east of the U.S. are Pennsylvanian, there are no angiosperms. Not a single angiosperm fossil has ever been found. So angiosperms are everything that's flowering plants. So maple trees, oak trees, tulips, almost every food we eat is an angiosperm, and every plant food we eat. And yet those are absent in the East, and they start to be present in the West when you get Cretaceous coals. And so, and Brian brought up these books, and I've read them. I've read these books. They are filled with false statements. And, what I encourage you to do is when you see something and they say, well, here's the reference that proves that point, read that reference. And what you'll find is a lot of the times the point they're making isn't supported by the reference that they cite. And the same thing with Dr. Brown's book. Start reading the references that he uses. What you'll find is he uses a couple techniques. One is he uses references that don't actually support what he says. Another is he'll use a reference from 30 or 40 or 50 years ago where there's more recent references that contradict that. They have more information. I mean, we've learned a lot in the last 60 years. And so when you put all the pieces together, there is prediction after prediction after prediction that has been made by plate tectonics, and it's already proven true. It's already proven true. And what predictions has Dr. Brown made about the Earth? I would submit, I went through that list. There's nothing that's actually accurate. I don't think he's made a single accurate prediction where he made the prediction and then it was found to be true about the Earth. I don't know anything about asteroids or comets or anything. And so it all falls apart when you have a decent geologic education. If you read it with a good high school education, yeah, it'll take you. And you won't understand where it's taking you down the false road. And so what I suggest is that, leaving it up to students to decide actually doesn't work because they don't have the background to evaluate what they're reading. And Dr. Brown's predictions, his list of predictions and how it fits with the hydroplate model versus plate tectonics, there are so many errors in that list where he says things that just aren't true and he leaves out critical information. How come Dr. Brown doesn't mention the earthquakes in the Mid-Atlantic Ridge that completely contradict what he says? How come he doesn't mention that that there were dozens of studies of reversing magnetic fields in lava flows on land that were done before they were discovered in the Atlantic? How come he doesn't mention that there are thousands of cores that have been taken through the sediments in both the Atlantic and the Pacific, and they can actually measure the reversing magnetic field as it's preserved in the mud, which is amazing, and that they've sampled the basalt, and so we know the basalt preserves reverse magnetic fields. So the whole story about the origin of the Atlantic just falls apart. What's the source of the basalt? In one of the diagrams of Dr. Brown's, he didn't even have basalt at the floor of the Atlantic Ocean. How did it get there? It's all not just basalt, it's pillow basalt, which is not the same composition as mantle. And so when you look at all of the evidence together and don't leave any out, the hydroplate theory falls apart, plate tectonics works. And, I wasn't presenting dogma. I didn't mention dogma
20 seconds.
Thanks. I presented data. And Brian did not contradict a single bit of data that I presented. Thank you.
Thank you, Howard. We'll reset the timer. Brian, I've got you unmuted. Let me know when you'd like to begin, and you have 5 minutes.
Well, I'd like to use Walt Brown's words in my closing. He wrote that Dr. Thomas Chamberlain warned researchers not to let one hypothesis dominate their thinking. Instead, they should always have or seek multiple working hypotheses so that we can think independently and not simply memorize and conform. Fruitful theories answer not only the obvious initial questions, but also solve perplexing and seemingly unrelated problems. Robust theories also provide details that result in surprising and testable predictions. If predictions are missing, the theory is probably weak. If theories could not be published unless they included many specific predictions, we would be mercifully spared many distractions and false ideas and wasted tax money. However, the plate tectonic theory dominates earth science as evolution dominates life science, despite growing recognition of their scientific problems because schools and the media ignore competing explanations. Earth science students are frequently discouraged from considering alternative explanations. Too often, students are told what to think, not taught how to think critically. Why is this? Before the field of geology began in the early 1800s, a common explanation for major geological features was a global flood. But many geologists were opposed to the Bible, which spoke of a global flood. So instead of appearing closed-minded by disallowing flood explanations, a more subtle approach was simply to disallow global catastrophes. Professors, primarily selected from those who supported the anti-catastrophe doctrine, did not advance students who espoused catastrophes. Professors also influenced, through the peer review process, what papers could be published. Textbooks soon reflected their orthodoxy. This practice continues to this day because a major criteria for selecting professors is the number of their publications. So the mantra is publish or perish. The anti-catastrophe doctrine is called uniformitarianism, where only processes observed today and acting at present rates can be used to explain past events. But Mount St. Helens showed that this was a poor and arbitrary assumption. So there's a dilemma. Because uniformitarianism is foundational to geology, should the entire field be re-examined to allow a scholarly consideration of evidence that implies a global flood? Most geologists object. They either deny that there's a problem or a problem exists, or hope it goes away, or redefine uniformitarianism. The problem's not going away. Ruling out catastrophes in general, and the flood specifically, even before all facts are in, has stifled study and understanding. Widespread belief systems seldom change when frequently reinforced by influential institutions, and when you're not allowed to think about anything else in class But when vast numbers of people realize that they've been misled, an intellectual revolution begins, like when Copernicus and Galileo showed that the Earth and other planets orbited the sun. And back then, as in today, fixed opinions will resist this shift in thinking because Thomas Kuhn wrote the preeminent book on how science works. In it, he shows that such monopolies continue in science, often for centuries, until startling new evidence arises along with a theory that better explains all the evidence. Then a slow re-education process begins, accompanied by hostility from those whose income, power, pride, and prestige are rooted in the old theories like uniformitarianism and evolutionism. Correcting these errors, now ingrained in the world's social fabric, will require a willingness by many to study, educate others, and follow the evidence wherever it leads. All theories should be subject to analysis, critique, and refinement. With theories and their predictions clearly enumerated, fieldwork becomes more exciting and productive. Most important, those who follow us will have something to build upon, and they will not be told what to think. Teachers, parents, and pastors have a simple, satisfying task: provide information, ask questions, challenges, answers, and allow students and congregations the excitement of discovery. Throughout the history of science, experience has shown that the simplest theory explaining the most details is probably correct. And with Walt Brown, you've got one theory with one assumption that logically explains 25 major features from mid-oceanic ridges to comets and asteroids. And when he said that he didn't make predictions about the Earth, he must not have read pages 447 to 449, because Walt clearly talks about, he predicted what they'd find under oceans. He predicted that they'd find V shapes in the Dardanelles and the Gibraltar and the Bosporus. And he's made a lot of predictions. So I encourage you to go to creationscience.com, go to 447 and 448, and see for yourself if Walt never made predictions that have been confirmed about the Earth. So, and this theory also makes astoundingly accurate predictions. It's being validated by NASA discoveries. And it's going to be interesting if Dr. Feldman would want this theory to be allowed in class, so people can have multiple working hypotheses, so they can think critically. Or would he rather just ram one thought process down their throats so they just memorize and conform instead of think critically? So I encourage you guys to see both sides, think critically, explore with open minds, and then enjoy the adventure. And you can start it going by creationscience.com. It won't cost you a dime, and you'll get all the information to make an informed decision. Thank you.
All right, gentlemen, that debate flew by. You both came in swinging. You both came in confident. You were assertive in your arguments, and the cross exam was very stimulating. I enjoyed that debate. We need to share this around to the audience, share this debate around. It's important that we get together with those that we disagree with. We get out of our echo chambers. We stand up to the mic and engage in these kinds of discussions. We've got two sides here: plate tectonics, the old Earth position, and then one specific global flood model, the hydroplate, being represented. And we got some good information here to digest and think on, that is for sure. So Brian and Howard, I appreciate your time and work. And now we got some audience questions. So let's see the thoughts of our live chat. What we typically do for the Q&A, gentlemen, is in order to move along smoothly, let's say the question is for Brian. We'll allow Brian to respond first, of course. Dr. Feldman, if you want to rebut anything that Brian said, or you want to add in your own thoughts, we'll give you that opportunity, and then Brian would get the last word. So whoever the question's for basically gets the last word. In organizing these, I think we got a pretty good mix of both. So we'll see. We'll start at the beginning. All right, let's have some fun. I want to see what our audience has for us. Scriptures and stones coming to us from the old earth position. He's got a question for Brian. Hydroplate theory has a major problem in that North America has multiple failed rifts from several Wilson cycles, such as the Real Foot Rift and MCR. You have any thoughts on that, Brian?
No, I don't.
Anything you could help us with that, Dr. Feldman? Maybe you got some thoughts or something you've studied there.
Just give me 1 second here.
Yep, take your time. To the audience, you can still send in questions and challenges.
Yeah, I'm not, I saw the Wilson cycle as a question in one of your other chats, and I have to say, I don't know what it is. I'm looking it up, and I thought I could understand it quickly, but I can't.
Yeah, that was brought up last night, actually. We had a session. And so, okay, let's move on to the next one. No worries. Redefine living in the house. Good to have you, brother. Question for Dr. H. Dr. Howard. How do you justify your uniformity assumptions when you also believe that each new layer is the result of a change in environmental pressures?
I am really glad to get this question, because there is just rampant misunderstanding of what uniformitarianism is. And it's partly our fault for not really defining it well. So back, a couple hundred years ago, uniformitarianism meant exactly what you said it meant, that you could explain all of the Earth's features with processes going on today. That is not what uniformitarianism means anymore. And this has been true since the 1960s. What it means now is that the physics of how things have happened hasn't changed. So if it takes a certain current to make a current ripple, and we see current ripples in the ancient, we can back engineer that there must have been those conditions. If it takes a certain velocity of water to move a pebble of quartz today in a flume, and we see that same kind of pebble in the past, we can work out the conditions. And so we're only claiming, there's nobody who's claiming in geology that you can explain all of Earth's history by modern processes. Nobody thinks that. Nobody has thought that for decades. This is something that creationists essentially have made up. What we think is that you can, if you understand the physics of how things work, you can apply those physics to the past. And so what we do, and what I did in the book, is every time we see a sedimentary structure, we know the conditions under which that sedimentary structure formed. And then if you have enough sedimentary structures, that puts a box around the environmental conditions that led to that unit being deposited. And sometimes that box is so small, there's only one option left, like a river or a beach or a delta. And so that's the way we do this. There's no assumption that it must be the same as it is today.
Thank you, Dr. Howard. Brian, over to you.
Well, and like in the opening, if you change the definition of when you're changing definitions, that makes you have less confidence in the theory. And Ron Neller, he said that, he was in 30 years, he's an evolutionist. And then he said, he's looking at all the world, and he says, there's a big flood here. And then he mentioned that, and then he had a lot of static about that. So they're allowing catastrophes at various places in the world, but they won't allow a worldwide catastrophe. So I would like to ask Dr. Feldman, do you think that a worldwide catastrophe should be an acceptable conversation in academia, or should that still be excluded?
It is acceptable, and it's absolutely allowed. For example, the asteroid that hit the end of the Cretaceous, that was, by any measure, that was a worldwide catastrophe. And
about
so
a
where the
worldwide flood?
data, let me finish talking, where the data shows that it is a worldwide catastrophe, well, of course it's allowed. But the problem is that there's no worldwide catastrophe that is needed to explain like the Devonian limestones or the Silurian limestones. And when you see soils in between them, you need to have time and subaerial exposure for those soils and river valleys to form. So there's no a priori assumption, and your statement of that is just false. And so, and there's plenty of examples of worldwide catastrophes. So they are allowed and they are published.
Okay, thank you, Dr.
I'd like to
Feldman.
hear Brian's response to that, actually.
Okay,
if
let's
there's-
do that. Well,
Yeah, the worldwide
another one. Go ahead.
catastrophe, that'll be, but they don't allow for a worldwide flood.
That's
You
not
start
true
talking
either.
about that, it's going to get really hairy in the world of geology.
That
And
is
as far as people
absolutely-
getting censored, Dr. Jerry Bergman's got 3 volumes of people who don't bow down to the sacred cows of evolution and plate tectonics, and they get fired.
There are absolutely worldwide floods. We've seen them many times, but there's
Oh.
also,
Really? Good.
yeah,
Good.
there's
Well, I
many,
agree.
many of them.
We agree
There's-
on that. There's been
there's lots
worldwide.
of them.
We agree on a worldwide flood. That's
No, well, there are many worldwide floods separated by sea level going down with river valleys and soils
So we agree that the world's been flooded at one time.
many times.
Right. But it was flooded. The whole world was underwater.
No, it's never been the whole world, but it's been lots of the world.
So it's not a worldwide flood.
Well, it's worldwide in terms of occurring over many continents at the same time, but not covering every bit of the continent. So if you look at say the Devonian, that's probably the widest flooding of North America. But there's still parts where there's mountains, and you can see the sediment being shed from the mountains in the Devonian, forming deltas. And so if there's rivers that are flowing downhill, there has to be mountains on the other side.
And marine fossils on Mount Everest. And so that was underwater at one time. You know, it
Absolutely
makes
it
sense
was.
yeah. So it would make, why couldn't there be a worldwide flood if Mount Everest has seashells?
Well, because it wasn't Mount Everest when it was flooded. It was much lower.
Right.
It's been lifted up.
Right. How do we know the whole world wasn't underwater when Mount Everest was underwater?
Well, first of all, it wasn't Mount Everest at the time.
I know.
And second of all, when you look at the district, I have to use a term called facies, which is a depositional term. And so when we look at the facies distribution, say in the Devonian, you can see where the shorelines were. You could see the deltas and the beaches that were forming at the shoreline. And so that proves that it wasn't the world. You could see the shoreline in the distribution of sediments.
Well, that could be as the flood was coming up, making those things, and then it went over the whole world. Because Dr. Ron Neller, you know, he concluded based on science that there was a worldwide flood. And then he said, you know what? The Bible talks about a worldwide flood. Maybe there is a God. And he brought that up. And boy, did that cause some static there.
Yeah,
and he
really
eventually became a Christian and he got fired. Should that have happened? Should they have fired Dr. Neller?
I have no idea what that situation, but it's really interesting to listen to both of us. I keep citing evidence. You keep citing people. I cite evidence. You cite people. Let's talk about
seashells on Mount Everest isn't evidence.
That is evidence, but it wasn't Mount Everest at the time.
Well, I know.
And
so what I'm saying is, how do you know that the whole world wasn't underwater when those sediments weren't underwater?
I've already told you, because we see soils and rivers, river channels at the same time. And so if you have a river channel, it wasn't underwater. You know, you had Dr. Werner on your show, and I disagree with almost everything he says. It's not that I disagree with this. There's evidence that disproves almost everything he says. But he did say one thing that is absolutely true. He said, how can river channels form beneath a flood? They can't. And I totally agree with that. And so when we see river channels in the rock record, like in the Morrison Formation and other places, it means the world wasn't flooded because there's rivers with soils.
Would you want competing theories in geology, or do you just want one taught as dogma?
I don't care what the competing theories are, as long as they're at the very least consistent with the evidence, which hydroplate theory is not.
Could it be allowed in class and let the kids make up their own mind? Or are you going to gatekeep that information from them?
If you fix all the inconsistencies and all the errors in that book, and I've got a list of probably about 100 of them.
Okay. Yeah, we'd love to see those because we'd love to get
I
fact
showed
checked.
that you could start with those diagrams of the continental edge
Well, yeah, those are general illustrations to give a general concept of what the slope is and the continental shelf. He's not doing details.
Well, even as general illustrations, they're wrong.
Okay, I'd love to see the other things. Yeah, we want to make sure we're telling the truth, and if there's stuff that's wrong in there, email it to me, and we'll get it fixed.
I didn't say that Dr. Brown hadn't made predictions of the Earth. I said he didn't make true predictions of the Earth. So let me give you an example. He claims that he predicted that there was a river channel, a V-shaped channel in the Bosphorus, right?
Yeah.
Okay. I challenge you to read the references that he actually cites and read some others. First of all, it's not a V-shaped channel, it's a U-shaped channel. So that's a big loss. He said it was eroded into crystalline basement. It's not, it's eroded into sedimentary strata. And Kenneth Asu made a similar prediction, but 17 years earlier in Scientific American, and you never mentioned that. And he used plate tectonics. So the one element out of 3 that he got right, somebody else beat him to it by 17 years. So I didn't say that he hadn't made predictions. I said he hadn't made any accurate predictions. And the record that he cites is distorted. If you actually go and read the citations that he uses to confirm those predictions, commonly they're not true, that the evidence that he's citing isn't in those references. And in fact, they contradict it. So there's one that he counts as a green, and it should be a red.
Well, how about when he predicted they find water under the mountains? How about that one?
Why is that a problem?
Well, he predicted it, and then they found it. You said he didn't make predictions.
I don't know why. I mean, there's water almost everywhere.
Well, nobody else predicted it.
Well, I don't know. It's such a trivial thing that why would there not be water under mountains? I don't understand where that's a problem.
Well, he made a prediction. The point is he made a prediction and it was confirmed. That's a far cry from him being wrong on everything and not making.
Well, that's a trivial thing because.
Well, you're going after his character. That's not trivial. You're saying he's a liar, and that's not trivial.
Well, there are many statements in that book that are false, like changing the size of Africa by 35%. That is not true. And he makes a big deal of it.
Well, he also made accurate predictions. And I'd like a list of the predictions, the current predictions of the plate tectonics theory. I'd like to see that.
Well, but there's already been so many predictions that were proven true. How many?
Right, but there should be current predictions so we can know if it's on the right track.
Well, I'm not a plate tectonics expert, so I can't answer that.
Gentlemen, this was an excellent back and forth round 2 mini debate. So Redefine Living, good job. You sparked some good discussion. Let's move to our next question. I'm sure several more of these will spark some more important discussion. Wesley Coleman has a question of clarification for Brian. He asks, so does HPT propose that the continents were not together when the flood initially formed the land masses?
Well, HPT, it's got the crust made of granite, and then there's going to be there's going to be the pillars sunk down, so they're going to be touching the mantle, and where they sunk down, there's going to be seas. And so, yeah, I would guess that they were connected at one time. Well, actually, they're still connected today. You know, they're not floating around on a lily pad there. Everything's connected. You just get rid of the water, and it's connected. So everything's connected.
So I guess to maybe help clarify as well with Wesley Coleman's question, would you say that the pre-flood supercontinent, Brian, was similar to what is portrayed in textbooks as Rodinia or Pangea, something like that?
See, I don't know. I don't know what it was like before the flood. I can see evidence of what happened after the flood, but I've got no idea. You know, a lot of it's just buried under sediment.
I think it also might help people because the positions today, plate tectonics from an old Earth perspective. There's also the catastrophic plate tectonics position, not represented here, and then hydroplate. So from that initial state to where the plates are now, how much movement took place when the fountains of the Great Deep broke open? Because would some consider that catastrophic movements of the plates, even in hydroplate, or?
Well, Walt Brown doesn't think that the Atlantic Ocean was there. Okay, he thought that all got eroded and then it slid away, and that's where that is today. Okay, so and then with catastrophic plate tectonics, you know, that's a secular model sped up. And if you listen to Dr. Tim Clary's talk, they don't have any explanation for all the salt in Mexico, that mother salt layer. I think he called it the Tejas salt layer, 1,000 or 2,000 feet thick over however big. He said that nobody's got an answer for it, where I would suggest that the hydroplate theory has a possible answer. And I think that it should be allowed in class so kids can discuss it. And I don't know.
It's way more than 1,000 or 2,000 feet. It's in places it's over a mile.
Right. Yeah. So hydroplate theory can explain that. I don't know if plate tectonics can. Catastrophic plate, Tim Clary said he couldn't. Can you explain how a mile of salt got under the Gulf of Mexico, Dr. Feldman?
Sure. It was evaporation, with more evaporation happening than seawater coming in. This is why you can't
60 miles, 60 miles of seawater went in there.
Yeah. I mean, the ocean's a big place, but it happened slowly over millions of years. So yeah, there's no problem. This is why you can't use the saltiness of the ocean as an indication of the age of the earth, because there's so much salt that has come out of the oceans.
I'm curious for myself, and then Dr. Feldman, feel free to engage it. Brian, you were saying that the Atlantic Ocean would not have been present. A lot of the water from the hydroplate model came from the fountains of the Great Deep. There's a displacement. So how much of the earth would you say? I'm trying to picture a lot of the sea creatures that we find, like Megalodon, Basilosaurus, Mosasaurus. Would all those marine organisms fit in your seas that would have existed according to the hydroplate model?
Well, yeah, I would think they would fit. How big it is, I don't know, but there was a whole lot more plants. I think, God made the earth to be inhabitable. Okay. And so there's a whole lot more plants. That's where we get all our coal from. Okay. That got pushed together and got squished together. And yeah, it's, I guess I'll leave it at there, but yeah, there was enough there. I mean, obviously there was creatures living there, and God gave them enough room to live. So how much of the earth, this is all speculation. You can't prove it either way. How much land and how much sea was there before the fountains of the Great Deep broke up? And we can guess, but we can't know. But what we can do is look at the earth after the flood, after the fountains of the Great Deep broke up, and then take a look at the predictions and see which ones students should be allowed to think about. Or not just whether or not we're going to allow students to think. Because if we don't give them two theories, we're just having them memorize.
Thank you, Brian. Howard, over to you if you had any thoughts.
Nope.
Okay, let's move to the next question. Very good. Very helpful. Our next question here comes in from Scriptures and Stones. Question for Brian. Does Brian think the Chinoomo quartzite of the Grand Canyon shows evidence of island coastlines with steep cliffs? Could the block be from shoreline erosion?
I'm not sure exactly which layer they're talking about, but the block was lifted up. How does erosion lift a 5 to 10 ton block lifted up into sedimentary rock? I don't think that's possible, no matter how many millions of years there is.
Thank you, Brian. Dr. Feldman, anything you want to add?
Yeah, sure. So I've looked at those photos. I've never been to that outcrop. When you look at the way the sediments are deformed, it's pretty clear the block was dropped down into that area. So not lifted up. And so, when you say that it was from this quartzite, that doesn't mean the quartzite layer is perfectly flat. There could have been a gradient to it. So it was higher in some areas and lower than other areas. And I actually looked into this. The only process that I know that can do this is one that's been very well documented in the modern, which is glacial dropstone. So glaciers, when they are eroding the continent, they pick up, hold on. When glaciers are eroding the continent, they can pick up large blocks. As they melt in the oceans, they drop those blocks. And when you look at the way the sediment is deformed, it's pretty clear that block was dropped down, not lifted up. And that's a process that actually we observe today. It doesn't require any special conditions.
Well, I
Thank
would
you.
say it looks
Brian,
like it's dropped down because it's heavy and it's in mud. So then the mud can't hold it all up. So it gets squeezed down into the mud. And as far as the glacier putting it there, glaciers aren't anywhere near there.
Not today.
No, not ever.
How do you know that? There's lots of glaciation evidence in the late Precambrian and early Cambrian. And remember, the continents weren't anywhere near where they are today. They were all different. And how do we know that? So there's a lot of ways we know that, but one of them is by looking at the paleomagnetic preservation in the lavas. And what they do is they point towards magnetic north. So then you can rotate the continent and you can figure out by climate patterns where the continents were and how they fit together.
So how come the Earth shifted? How come the Earth shifted then? If Mount Everest couldn't shift it, why would anything shift it?
I'm not talking about shifting the world. I'm talking about moving continents through plate tectonics.
Okay, well, Dr. Hamilton said that the convection theorists, they can't move them. Is what a Nobel or a Penrose Award winner says.
Yeah, Penrose. You described the Penrose accurately, and I'm not familiar with that paper, so I can't comment on it.
How many
your
Penrose
description of the Penrose medal is accurate?
Yeah. Well, how many Penrose Award winners did you take classes with?
None.
Well, Walt's got you beat there. He's got one.
Okay.
Gentlemen, very good. Let's move to the next question here. Comes in from Why Budry for Dr. Feldman. If granite was formed under liquid magma, why didn't it turn to rhyolite?
So, so we have different names for the igneous rocks based on two criteria. One is the mineral composition, and the other is the grain size. That is, how big are the crystals? And so with basalt, if it's fine grain, we call it basalt. If it's coarse grain, we call it gabbro. With rhyolite, if it's fine grain, we call it rhyolite. The exact same mineral composition. If it's coarse grained, big crystals, we call it granite. So with granite, there are, it takes a long time to cool in order for the big crystals to grow. So that's been documented in labs, although you can't cool it slow enough in a lab to get the size of the crystals that we observe. But there are other things that we do observe. For example, you can show that the different minerals have different melting temperatures, and that by cross-cutting relationships, you can show that the crystals that have the highest melting temperatures form first, and the minerals with the lowest melting temperatures form last. You talked about minerals settling out of suspension. That absolutely has been observed in modern granites. Not very commonly, because granite magma is extremely viscous. This is something that, again, can be measured in the lab. Basaltic magmas are not viscous, but granitic magmas are. And then there's a lot of places where granite has been injected into dikes, and we can see contact metamorphism, so we know that it was hot. And there's also a batholith is a large body of granite that may be tens of kilometers wide. And then around those bodies, it's very common to see metamorphic zones of decreasing metamorphism away from the batholiths. So that, again, is indication that you're getting cooler away from the batholiths. So there's all sorts of evidence that they were liquid magma at one time.
Thank you, Howard. Brian, anything you'd like to add?
Well, Dr. Robert Gentry, he'd disagree with you because there's radiopolonium halos in the granite, and he says that's like finding Alka-Seltzer bubbles in ice. It cooled quickly. It was formed quickly. And he says you can prove this wrong by making a handful of granite with those polonium halos in there. And then they found out that went against their billions of years thing, so they cut his funding. Another way to look at it, too, is with Walt Brown. He says that if granite was ever liquid, then it's made of mica, feldspar, hornsplit, and quartz. They all have different specific densities. So if it was liquid, you're going to get the heaviest one to settle out first, and then the next one and the next one. It should be layer cake. And it's like, so therefore, granite was never molten.
So they wouldn't settle out in the order of density. They would settle out in the order of crystallization. That
so it should be a layer cake.
As the temperature decreases, you're going to get the minerals with the highest melting temperature freezing first, and then the lowest melting temperature is freezing last. But because the granitic magma is so viscous, as they form crystals, they actually form a lattice work inside that, so that it's very difficult for them to settle out. And you can actually see this when you look at, say, a granite countertop, and you look at the crystals that are well formed, they have high melting temperatures, and the crystals that are poorly formed, like quartz, have low melting temperatures. But there are places where you can see that the crystals settled out in the order in which they precipitate, or not precipitated, in the order in which they froze. It's not very common, but it absolutely does occur.
Brian, anything you wanted to add, or should we move on, gentlemen?
Yeah, I would suggest until you can make granite, you don't know how it got there. And until you can make it, I would say that's what God made.
How did gabbro get made? Is that also a miracle?
I don't know. And that's what it's really coming down to, is where did everything come from? Where did the plates come from? Where did the granite come from? Where did the water come from? You think it came from asteroids?
I don't know.
See, we both have belief systems about the past.
It's not a belief system. Everything I presented is evidence.
Except you don't know where it came from. That's a
Well,
belief system.
there's no guarantee that we've solved every single problem in science. If there was, we'd stop. We'd be done.
But if you disallow a creator, what if the answer is outside of material naturalism, methodological naturalism? What if the answer is outside of there? What if there's actually a supernatural creator that made a natural creation? If scientists aren't allowed to look that way, we're going to come up with a bunch of crazy ideas like junk DNA and vestigial organs.
Well, I don't know anything about DNA. What I do know is that the scientific method doesn't allow for that. And this has been highly successful over the hundreds of years that we've used the scientific method.
Right. And it's observable.
As soon as you allow for miracles, you end up with God of the gaps. And you just, every time you come to a problem you can't explain, it's a miracle. And that is not the way science works.
Well, if you don't allow for God, now you got to break laws of physics. You got to have matter from nothing. You got to have life from non-life. You got to have information from matter. You got to have consciousness from matter. Everybody believes in miracles. Some people have a miracle maker, and then other peoples don't have a miracle maker, and they won't allow anybody who does believe in a miracle maker, they'll shun them. And they won't allow them to think about it.
I never said I didn't allow for God. I said I didn't allow for miracles in the scientific method. That's very, very different.
Okay, with the scientific method, where did matter come from?
I'm not a physicist. Let's stick to geology.
They don't know. How did life begin? Nobody knows.
Gentlemen, let's move to another question related to geology here. Static 412, thank you very much. Question for Dr. Howard. If the layers were formed over millions of years and each layer represents a time period, why can we find huge trees buried in rock layers vertically, polystrate trees, I think he's referring to, through the layers? What are your thoughts?
Okay, so, this is a problem that I've seen a lot of creationists make, is that we say, well, these, this huge thickness, like the Grand Canyon's a mile deep, and we say, well, that formed over whatever it is, 200 million years or whatever. And then you say, okay, well, that means this 1 inch bed must have formed over 1 million years. No, it doesn't mean that at all. You can't just take the average depositional rate from some huge thickness and divide it down and get something that approaches anything that's reasonable. So when we look at upright trees, and I've studied outcrops with upright trees, and I've published a paper on upright tree. Well, it wasn't specifically about upright trees, but it was about deposits that included them, and we described them in the paper. They require very rapid deposition. In fact, the trees that we looked at in the Pennsylvania and Kansas had attached leaves on them. We didn't have any photographs of them in the paper because it just wasn't conducive to photographing. But there were attached leaves, no problem. And so very high depositional rates. And so when you look at all the evidence, you end up with episodic deposition. You end up with very rapid deposition, then erosion, then rapid deposition, then erosion, then rapid deposition. And this happens over and over again. And what you're seeing in the rock record are the last cycles of rapid deposition. And occasionally you see sediments that were deposited slowly. So we take the deposits with the evidence that they come with. So if the evidence says they were deposited rapidly, that's fine. There's no a priori assumption of slow deposition. So there's no contradiction.
Brian, any thoughts?
Well, yeah, there was a rapid deposition in the past, and I would point to a worldwide flood would do that, because you got billions of dead things buried in rock layers laid down by water all over the world. And some of that sediment was big enough to bury mammoths or to bury the dinosaurs. So if you allow catastrophes in the past, I think we should allow for a worldwide flood. Because those sediments that you need to make fossils are not being laid down, according to Ron Neller. It's like 0.5 millimeters in the ocean floor over 1,000 year or a year. And in the bays, it's like a few centimeters. And you need, yeah, and the biggest typhoon ever measured laid down 10 centimeters. And that's not enough to fossilize an alligator or anything.
Well, first of all, you're ignoring all the evidence from soils and all the evidence from river valleys and all the evidence from river channels that are in between those flood deposits. And that invalidates a single worldwide flood. Second, I don't know who this guy is, but he's absolutely wrong. I understand modern sedimentology. There is absolutely places where you get high enough depositional rates to bury and preserve whatever is there. And to say that you don't get that is just blatantly ignorant of the evidence from modern depositions. If you go to the mouth of the Mississippi River, depositional rates are really high. And so we see a lot of places around the world where you get sufficiently high depositional rates to preserve whatever it is you want to preserve. So that's just blatantly false to say that doesn't happen. And you're ignoring, I'm accepting all the evidence for worldwide floods, and you're ignoring all the evidence for the time between the floods when soils and river valleys formed. And I've mapped these river valleys. I've published on them. We use them as an exploration target in petroleum. They're widespread and they're common.
Can I share my screen, Donnie?
Yes. Yep. You're good.
Okay, this is what Ron Neller was talking about. He'd been in the industry for 35 years, and this is the sediment that's being laid down in the oceans. It's the red is 0.5 millimeters a year. So they said go farther inland, and so then he went into this estuary or this the shelf here, and they found that it was an average rate of 300 millimeters for 1,000 years. And that's not going to do it. And then he went to this aquarium, and it was 0.6 millimeters a year globally. So this is what he's saying, and he's got his PhD in fluvial geomorphology. So that's what he does. He studies floods, and this is what he comes up with. And so I encourage people to listen to Ron Neller. He just check the correct shit. Listen to that on YouTube, and listen to again. Be fair. Listen to Dr. Feldman, and then you can see both perspectives. And that's basically why I'm here tonight. I want people to see both sides and then come to their own conclusion. What bothers me is when they don't allow both sides to be presented. They say this is the only way you can think. And that bothers me because we don't need people to memorize. We need them to think.
Well, this is cherry picking the evidence. There's plenty of places where you have a meter a year being deposited, and there are tidal cycles preserved in estuaries. I've trenched them, and you can count the tidal cycles, and you can determine very accurately how much sediment is being deposited each year. And so, yeah, there's places where there's not very much sediment being deposited, and there's lots of places where there are. When we looked at that tidal flat in Kansas that we published on this, the first author was Bill Lanier, a colleague of mine at the time. This is 30 years ago. We were able to count the tidal cycles, and we determined that this one outcrop that was about 3 meters high with well-preserved plants, and it was deposited over 11 months. And so by counting the tidal cycles, you can go to the modern environments and do exactly the same, and you can show high depositional rates. So, I'm a little bit familiar with what he's done, and I don't know how he ended up with those rates because I've been to similar environments where you see very rapid deposition. If you average it over a long enough period of time, it'll appear slow. If you average it over 1,000 years, it's going to look really slow. But if you look at how much sediment is deposited from Monday to Tuesday, it can be very high.
Well, those things were showing so much per year. Okay, so again, there's
different
views, and I just encourage people to see both sides. That's basically all I want is people to think and see both sides and not censor people.
Howard, you can have the last word if you'd like. That it was for you, the question.
What was that? I'm done.
Okay. LD Drosophila, thank you very much for the super chat support and question. Drosophila, yes. $5 super chat question. So it looks like it's a question for you, I think, Howard, because she's coming at it from the old Earth position. And she's wondering recommendations for your favorite place to see geology for a layperson interested in the ancient world here in the U.S.
Well, there are some great places. I was talking to Donny before we went on the air I would love to lead a field trip for creationists. And one of the great places to do this is in Green River, Utah, in that area. There's lots and lots of outcrops. There's both Cretaceous and Jurassic. There's beautiful river channels. There's some pretty good soils and lots of other deposits. But you can't do it without a guide. It's really hard to do this without somebody to show you, what the important features are. Like it's really hard to see burrows if you don't know what you're looking for, to see erosional surfaces, and also to find the outcrops. Like, I've been leading field trips both for Exxon and for other companies to that area for a very long time, And so I know the outcrops very well. I'd be more than happy to lead a field trip for people that are interested. We wouldn't be looking very much at fossils. A little bit. There's some really nice dinosaurs buried in the area where we can look at the evidence for deposition. But it's also a very pretty place to go. And so that would be, and the main reason I'm recommending it is just because I know that area very well.
I do think that would be fun, where you get a group of creationists, group of evolutionists, those on the opposing side, field trip looking at these formations and fossils and so on in person, having some good discussions. Who can explain these observations better? Which model? Brian, anything you'd like to add there?
Well, if you want to get a quick overview of the hydroplate, you can go into my YouTube channel called Solidify Your Faith, and I've got a playlist specifically for the hydroplate where you'll see a 2-minute animation, an 8-minute explanation by Dr. Walt Brown himself, and then a 2-minute video showing how NASA is confirming the hydroplate. And then I'd encourage people to go into Real Science Radio. That's rsr.org. And when you're driving around, listen to those interviews, whatever topic, dinosaurs, earth science, whatever. He interviews people and they do really well. And then I'd also, hydroplate.org is a good repository. And then the brand new one, hptuniversity.com, or on YouTube, you can see Hydroplate Theory University. And again, it's a theory that's, I think at the time is coming. The party's coming. It's just a matter of, are you going to be early or late? And those are some good sources. Yeah. Oh, also we did a hydroplate conference in 2023 that you can see on YouTube. It's at the Hydroplate Theory channel, or otherwise the Hydroplate Theory Week of Celebration, where you can hear a bunch of PhDs giving talks and also personal experiences with it. And again, people get excited about this theory, and I can talk to college students for an hour and keep their interest on this. And again, people want to think. Give them 2 theories. That's all I'm asking for. Let's allow 2 theories in class and let the students think. Would you agree with that, Dr. Feldman?
I would not agree with allowing a theory that has so many deep flaws and contradicts the evidence so deeply.
Gentlemen, okay, that's a good place to move on to the next one. I think this is for you, Brian. Comes in from Jedi FPV. Actually, no, I think this might be for Dr. Feldman. What precise mechanical process allows a subducted slab to penetrate the 660-kilometer seismic discontinuity into the lower mantle?
Yeah, so just to bring everybody to the same page, the 660 discontinuity was discovered by ray tracing of earthquake waves. And as you increase the pressure in the mantle, there's a reorganization of the crystal structure that becomes more dense at 660. And so then there's a question of, can mantle movement go up or down through that boundary? And it's not clear. It's still up for debate. The hot spots appear to go through that, and they've been actually imaged with tomography. So there appears to be, you can have material going up through 660. And then when you image the subducting slabs, of course, as you get down that deep, the images get poor, but it appears that sometimes the slabs will go through that contact, and sometimes they'll kind of crumple when they hit that boundary. So, the old version where there was mantle convection from the core up to the spreading centers and then back down to the core, that's pretty much been abandoned. And so now the 660 boundary seems to divide the mantle. So there's convection below that between the core and 660, and then there's convection from 660 up to the lithosphere. But there's also a lot of uncertainty with that. the data is not clear cut at this point.
Thank you, Howard. Brian, over to you.
Well, he had mentioned the scientific method earlier, and that's observable, testable, repeatable, falsifiable, and subduction is none of that. And until they can get that figured out, that's a big showstopper for plate tectonics. And there was something that came out a year or two ago. There was a discovery of some big mass that wasn't by any of the boundaries. It was like in the middle of the plate, and it shouldn't have been there. Kevin Lee wrote this wrote an article on it, and I think it might be at calvarypo.org maybe. But yeah, there's some things that go against plate tectonics. But when the plate tectonics proponents, they control the journals, people aren't going to hear about it. And you won't even be allowed to have it in class like you've seen here, even though it makes accurate predictions. And NASA discoveries are validating it. It's still going to be censored from the kids. Is that right, Dr. Feldman?
Well, I don't call it censoring. I think there's, I showed how many examples do you want where the statements in Dr. Brown's book are false?
Well, how about the accurate predictions? How about him predicting what they'd find in a comet and an asteroid? Those are astounding.
Like I said, I have no expertise in comets, but I already talked about the Bosporus where he claims a successful prediction there, and it's wrong. He's not successful. He's
been successful with comets and asteroids. Shouldn't that be looked at?
I can't, when I've looked at the predictions that I've made where I understand what they're talking about and I can easily look it up, it doesn't work. And you're talking about things where I don't have any expertise, so I don't have any way to.
Well, you watched a lot of my videos. You can check out those sources. Rounded boulders and Comet 67P. You've got
you never provided a publication date or source for the inaccurate predictions by the NASA scientists. Not that I saw.
What's that?
If you say that NASA scientists made inaccurate predictions, where's that publication?
It's there. I show the video. I give sources. Yeah, go into Kevin Lee, Pastor Kevin Lee, and he gave a talk at the Twin Cities Creation Science Association. You can look at that on YouTube, TCCSA, and that's also the talk that he gave at hydroplate.org. He was face to face with the NASA scientist. And he said, with that Stardust mission, you're going to find stuff from the Earth. And that guy says, no, we're going to find stuff from the Oort cloud. And Pastor Lee was right, and Walt Brown was right. And then he contacted the same guy, Dr. Brownlee, and he said, if you try to redirect an asteroid, it'll work if it's a solid block, but if it'll fail if it's a bunch of boulders. And it turned out to be a bunch of boulders, which is exactly what Walt Brown had predicted. And so if a theory is making accurate predictions, I think it should be worthy of consideration. You don't have to endorse it.
Where are the accurate I'm an Earth scientist. I really don't know anything about asteroids.
Well, it's about freedom of thought. Do you want the kids to have freedom of thought, or do you want to force feed a theory down their throat?
Of course, but the theory needs to at least be consistent with the data we have. And I've shown you so much data that is inconsistent with hydroplate theory.
But it makes accurate predictions. That should count for a lot more. Accurate predictions is the currency of science. And he's been right, and he's been confirmed. And every time NASA finds something, it seems like, I have this T-shirt, Walt Brown works, or NASA scientists work for Walt Brown. And
but again,
if the theory is false.
But again, when I've looked into the alleged accurate predictions about the Earth, they don't hold up. So I don't have a lot of faith that what you're saying is true.
Okay, well, we'll just.
And I'm frankly not going to spend the time. It took me a long time to gain the expertise on subduction and rifting and all this, because it's not my area of expertise. My area of expertise is stratigraphy and paleontology. And, the more I looked into it, the more problems I saw with Dr. Brown's theory. What do you have to say about his claim falsely that Africa was changed by 35% in size in order to get plate tectonics to work?
Well, I don't know. I don't know about that, but
it never occurred to you to look into that?
Are you going to be, you don't have to be an expert in a theory that makes accurate predictions, but you can look into that. Are you excited about a theory that can make accurate predictions?
I have looked into the predictions. I looked into the predictions that were made about the Earth, and they fall apart. So there's only so much time I'm willing to devote to this topic. And, I know an awful lot about the geology of the Earth. And as I read this book, my stomach churns when I see all the false statements. And then he says, here's the citation. And you go 30 pages I find the citation, I read it, and then what he claims isn't validated by the citation he uses.
Well, I'll
give you another example. He claims there's superheated water vents in the Gulf of Mexico. And when you read the citations that that's based on, there's no such information.
Well, I showed you the one for the Atlantic. Well, Bob Enyart, he did go through all those citations. He did look at all of them, and he said maybe 1 out of 60 he had to tell Walt, this one you got to fix. So someone did go through that.
Well, way more than that.
Okay, well, that's again, we just want people to think. But when you won't even allow a competing theory, I think that's hindering science.
Don't you agree that any competing theory at the very minimum needs to be consistent with all the evidence?
Well, and I would say that if it makes accurate predictions, you should put it at the front of the line. A professor asked me one time, hey, what would you do if you were the king of science for a day? I said, we'd put all the theories on the table and we'd focus on the ones that make accurate predictions. Plus, we won't teach belief systems about the past, like the Big Bang and evolution. Well, we just deal with science, where we can observe and test and repeat the scientific method.
Your description of the scientific method is misleading, I'll say. There are, we can use the scientific method in the past by making predictions, and that has been done many times in the past. I can't tell you about plate tectonics making predictions today because it's not my field, but certainly I've made in my career many predictions about what we'd find by drilling oil wells. And I've been right more than I've been wrong. And,
well, so has Tim Clary. Tim Clary's found the oil too, and he's got a creation perspective. You can have a creation astronomer and evolutionist astronomer, and they can both get an astronaut to the moon, but neither one can prove how the moon got there.
I can give you a list of all the false statements in Tim Clary's book too.
Please, I want to see them. We want to get that corrected. If there's things that are wrong in there, we want to get it corrected. So if you can send me a list of them, we'll correct them.
Are you going to advocate correcting Dr. Brown's book so it includes all the evidence of soils in between the marine deposits?
Well, I want it to be an accurate book. If there's something wrong in there, we want it fixed.
There's lots wrong. Everything it says about
send us the stuff. If we can get fact checked for free, absolutely.
I've already shown you several diagrams that are so faulty.
That's your interpretation of it. But we'll take a look at it.
I didn't talk about my interpretation. I showed you a seismic line and we compared it to the diagram. And the seismic line is different than the diagram.
Gentlemen, I'd like to continue these thoughts, but let's do so with a couple super chats that came in that were inspired by this last round of discussion. I appreciate it. So Static, $5 super chat. And you can continue right along these lines, Dr. Howard. He's asking, why not let the hydroplate theory be taught if you value free speech?
I've already discussed this head on. It's not consistent with vast amounts of data. And so that is, to me, the bare minimum of any theory needs to at least be consistent with the data that we have. And it's not.
Brian, anything you'd like to respond to?
Well, then you could show that in class, this is what bothers me the most. You won't allow it to be talked about. And if somebody does bring it up, they get thrown out on their head. That's not science. And yet you teach evolution and say that, hey, millions of years of chemicals banging in together can lead to life. And Jonathan Sarfati says, no, it can't. Hydrolysis breaks it apart. So can we at least agree to try and get the errors out of the textbooks that are in there now? Would you like to help that process of getting people good information? If you don't want Waltzbrook taught, well, what about the textbooks in high school? It's riddled with errors that they're teaching as fact. And would you join me in trying to get those errors out of this high school textbooks?
Well, I have to look at what errors you're talking about.
I've got a talk called Errors in the Textbook. I gave it at St. Cloud State. And it's in my college one, or I gave it several times so that it's in my YouTube channel. You can even look at my school board messages. I went to the school board to try and get them out of there. At first, I talked to sent the message to the curriculum director, and I showed him all the errors.
One error.
And then I showed him like 6 or 7 errors. And she said, we're just teaching the state standard. And I said, well, what standard says we're 1.6% different than chimpanzees? And she didn't email me, but the superintendent did. And did she say, yeah, we're going to look into this? We'll contact the publisher? No. She said, we contacted a law firm in our response. And so then I went to the school board to see if they'd do something about it. I went in there thinking that, hey, we want accurate predictions, right? And I walk away saying they don't care. They'll teach what the state standards are, even though the standards are wrong. They still want the Haeckel's embryos. That's the state standard. They have to show that the embryos look like each other, and that was proven wrong 100 years ago. So if you're against Walt's book because it's got errors, man, you should be against those high school textbooks that got errors, and they're probably in the college textbooks too. Can we join forces, you and me, and get the errors out of the textbooks?
Well, you're talking about errors in which I have no expertise. I don't know anything about genetics. I don't know anything.
Do you pay
about
taxes?
genetics.
Do you pay taxes? Do you want your taxes being used to tell kids lies?
Of course not.
Okay, well, this is what's happening.
But it's your impression of what's a lie. That may not be the same as mine.
Gentlemen, very good. Next question. Wesley Coleman Music, $10 super chat. Before I read it out, this Q&A has been great so far. This is why I tell people that the debate doesn't end after the closing statements. In a way, the fun's just getting started. So really good. Wesley Coleman. Dr. Howard is willing to, he's coming at you a little bit, Dr. Howard, dogmatically accept everything he's not an expert in. Do you think that any of those interpretations impact his field of expertise? Howard, feel free to respond.
I'm not sure I understand the second part. I've got an awfully broad knowledge of geology that I've gained through being in the petroleum business. I haven't dogmatically accepted anything, but that doesn't mean I have time to investigate every single claim that's ever been made about geology. I've certainly looked at a lot. And what really impresses me is how little what is said about geology in the world of creationism is correct. And I listened to a little bit of your discussion last night, and with what's the name?
Sal Jardina.
Sal Jardina, thank you. And like what he was saying about river channels in the rock record, far removed from the evidence. And so this is what motivates me to come on shows like this. And I'm willing to debate anybody on the stratigraphic record. There are certain elements of the stratigraphic record that are inescapable, and it's not dogma, it's evidence. The soils in between and the marine units, the river valleys in between the marine units, evidence of rooting and bioturbation that takes a long time. You just can't fit it into a 1 year cycle. And certainly, I've read everything that was in Dr. Brown's book about sedimentary rocks, and I'd say 2/3 of what he says just isn't true. Limestone isn't created chemically. Most limestones, there are some that's created chemically, but most limestone is created by fossils. And so it doesn't come from the fossils of the deep. It comes from organisms living, making shells. And we can see that process happening today. And so, there's no way that any one scientist can independently investigate every claim that's ever been made. But I did spend years working on this. And so I stand by what I say. And if somebody has data that says what I'm interpreting is wrong, I'm happy to look at the data, but only within my area of expertise. I'm just not willing to spend time looking at retroviruses or DNA or asteroids. It's just too far out of my expertise. I don't know if I've answered that question because I'm not sure I understand the second part.
Well, I do appreciate you interacting with it. Brian, anything you'd like to add to that?
Yeah, I would like to say that this is what happens when only one theory is allowed to be taught. People just blindly, they don't have another option when they're going through school. And that's what I encourage people to go listen to Dr. Ron Neller. He's a CMI speaker, and he was a geomorphologist. That's what he did for 30 some years. And the evidence had him conclude that there was a worldwide flood. And so then he said the Bible talks about a flood. Maybe there's a God. And so then an atheist brought him, he's an agnostic, and they brought him to church, and they both got saved. And then he became a Christian, and then he got fired. Should that be happening in academia? I mean, there's 3 volumes of this. That's what happened to Dr. Jerry Bergman. He became a Christian, and they fired him, and he had everything going for him. He had more published publications, and there's 3 volumes of that. Can we fight for freedom of speech on campus, where people don't have to bow down to the sacred cow of the Big Bang and evolution? Would you join me in that process? where people can have competing hypotheses? Or does that have to go through the gatekeepers at the government too?
Not gatekeepers of the government, gatekeepers of evidence.
But should people have competing, should there be competing theories like Dr. Thomas Chamberlain said? Always have or strive to have multiple working hypotheses.
Multiple working hypotheses is a cornerstone of science.
Well, not when you exclude the hydroplate. What's the other option for plate tectonics? What's the other competing theory for plate tectonics?
I exclude hydroplate because it contradicts with the evidence. You can't have paleosols and river valleys in the middle of the stratigraphic succession and hydroplate.
So what's the other working hypothesis that competes with plate tectonics?
I don't know.
There isn't. Yeah. So they're just memorizing.
Well, but you need whatever working hypothesis you have has to be consistent with the data that's already been collected. And that's not true with hydroplate.
So we should get rid of evolution then too. How did that life begin? I mean, there's a lot of things that.
Brian, if you want to debate the fossil record, bring it on. I'm all there. You let me know.
All I'm doing here is I want freedom to think. I want multiple working hypotheses, like Dr. Chamberlain says.
You're willing to take swipes at evolution, but you won't debate me on the fossil record? I'm willing to do that.
Well, maybe we should. Because there should be multiple working hypotheses. And you agreed with that, but there isn't one for plate tectonics, so just take the hydroplate.
There are multiple working hypotheses for the circulation of the mantle. There's multiple working hypotheses for house subduction. I already said that. There's the hypothesis that you have mantle convection from the core.
Well, it's all based on plate tectonics. What's the opposing view of plate tectonics? What's the competing view of plate tectonics?
Well, you'd have to come up with one that's consistent with all the data that's already been collected, and that hasn't happened.
Well, I think Walt Brown has done that.
No, he hasn't. How many pieces of evidence do I have to show that he can't account for? And that contradict statements in the book, contradict illustrations in the book. I mean, I don't understand why you still say that when I've shown you seismic diagrams of what continental edges look like, compared them directly with the evidence that he presents as a typical shelf edge, and they don't agree. They're not even close.
Well, I'm skeptical, okay? And I've got a right to be skeptical.
You do.
Because 100 years ago, the experts were telling us Piltdown Man was a transition, and it turned out to be a chimp skull, or a skull of a human and a jaw of an ape. That was wrong, but it was in the textbooks for 30 years. 100 years ago in 1926, they were telling us this tooth was from Nebraska Man. The experts were. Yeah. Okay, and then a few years after the Scopes monkey trial, then they said, no, it's a pig's tooth. And then they're telling us there's vestigial organs. They're just left over from evolution, and they were wrong. They're telling us that it's junk DNA that's got no purpose, and they were wrong. And then what really gets me is the experts are telling us during COVID all this stuff that was wrong. So as pardon me from believing anybody that says, trust me, bro. No.
I'm not saying trust you. I showed you the seismic images, and those are absolutely typical of what you see. I'm not saying trust me ever. I didn't say it once.
Well, seismic images, could they be fraudulent like Piltdown Man? Is that a possibility?
No, they can't be fraudulent. I'm telling you why they can't be fraudulent, because this is what the oil companies use to explore for oil. Anybody who was caught selling fraudulent information would be fired or sued. I mean,
you would think that would have happened 100 years ago, anybody promoting fraudulent information, but they did get fired. The one who came up with the tooth for the Scopes monkey trial, he got awarded. He got the biggest award in North America.
But Dr. Feldman, feel free to finish.
This is economics. This is what oil companies do. They pay millions of dollars for this data set. They use these data sets to drill wells. Wells cost hundreds of millions of dollars to drill, offshore wells anyways. And so there is no chance that these lines are fraudulent. I mean, there's hundreds of them. And this is the bread and butter of petroleum geology. This is what I did for 30 years. And so, and we've got, we drill the wells, and so we can compare the results from the well with the seismic. So is it fraudulent? Not a chance. Is it 100% accurate? There's always inaccuracies whenever you collect data. But it's not fraudulent. No.
It's always assumed that it's uniformitarian processes. It could be quick river draining too, couldn't it?
I don't know what a quick river is.
Well, That's
I mean,
because
do
you
you
have
want to see some?
uniformitarian glasses on. If you had a flood model glasses on, you could have a big tidal wave go in there and drain it down, and have another tidal wave drain it down and make a different
No,
river
that
bed.
wouldn't. That's not consistent with the sedimentology. The sedimentology puts constraints on those processes, and so I could show you. I've got backup slides I haven't shown. If you want, I could bring up a slide that compares what a modern river looks like with what a seismic image of an ancient river looks like, and they're identical. And when we look at the sedimentology, when we core it and we look at the sedimentology, we see that the sedimentology is identical to modern rivers. And yet there's marine deposits below the river, there's marine deposits above the river deposit. And so and the point bars that we see take hundreds of years to form. There's no process that you can do. It would violate physics to try to get it to go faster.
Well, it would violate physics, in my opinion, to have sea level rise and fall dozens of times.
Glaciation does it. You don't need the physics of that's well
But
understood.
you don't know how glaciation started, and once it started, it shouldn't end.
There's a difference between understanding how something works with understanding that it happened.
Well,
I can
Neller,
drive my car without understanding how the engine works. We can see the evidence for glaciations without understanding how all the cycles work.
well,
But
Ron
the
Neller
evidence
was in Finland.
let me finish. The evidence that glaciers happened, multiple glaciers happened, is so solid. It's hard to come up with an understanding that wouldn't involve that. And so that process allows for sea level to go up and down. That's all you need. And so it's a process that we can observe happening today as glaciers melt and sea level goes up. And we've got evidence that it happened in the past, and we can match the oxygen isotope cycles to the sea level cycles we see recorded in the shelf edges. And the work that I did in the Cretaceous of Canada, the best hypothesis I know of to explain those cycles is glacial cycles in the Cretaceous, but it does require time.
Okay, well, I would encourage people to listen to Ron Neller, because he was in Finland and he took a look at these glaciers, and what he saw was one glacier, one ice age, but there was, hundreds or dozens of glaciers. And he said, why would they do that? Well, wouldn't you like to have an ice age named after you? And so there's two perspectives of the same evidence, and I'm banging the drum to say, let kids see both sides. Because I started in the opening statement, I read a bunch of critiques against Hydroplate from Penrose Award winners and PhDs, and yet that's not in the science books. It's taught as fact, and it's not. There's some strong arguments against it, and the kids aren't allowed to see those arguments in the textbooks. So then they're just going to swallow it hook, line, and sinker, and I think that's hurting us, hurting science.
Howard, I do want you to respond, but if you could, in the context of Wesley Coleman's follow-up super chat, Wesley, $5, I appreciate it. So therefore, Dr. Feldman, if there's anything you'd like to respond to there from Brian, feel free to do so, and this at the same time, since it's all kind of on the same topic. So he says, Howard, you are not a neutral interpreter if you accept teachings you have not dug into. Those teachings impact your interpretation of your expertise. Feel free to engage that if you'd like.
Yeah, I think I've already addressed this. It's impossible to track down every claim that's ever been made in any science. I'm pretty knowledgeable about the area of stratigraphy and the fossil record and biostratigraphy. And so, when I come across things that don't make sense, I do look into them, but there's also a limit to my time. I'm not going to look into genetics. I'm not going to look into asteroids, just because there's a finite number of hours in the day. I think I've addressed this question pretty thoroughly already.
I'll hand it to you, Brian, for a response. And I think you did just respond to this follow-up question, Dr. Feldman, that I have for you. But if you'd like to, feel free to reiterate it. I think when you're explaining modern rivers versus some of the channels that you find in the fossil record, like in the Morrison, but how would you respond to a creationist who says that flood geology, whether it's HPT or CPT, predicts localized erosion, scouring, and channel formation as a response to some of those features you've pointed out?
Yeah, can I share my screen?
Yes. There you go.
I'm not sure what that is.
Oh, is that the wrong screen?
Let me share from scratch. Sorry.
Okay. Start fresh. No problem. To the audience, I am caught up on the new super chats that have come in. I appreciate it. Gentlemen, this stimulating Q&A has generated a lot of follow-up questions, so I appreciate you guys being good sports and interacting with them.
So here's an example. Do you see it? Yep, there you go.
Yeah.
So let me just expand this a little bit to fill the screen. I'm not going to put it in display mode because that would go to a different monitor. So on the right is a LiDAR image. This is where you use lasers to get a very accurate image of the Earth's surface. And this is the Mississippi River, and this is a bend in the Mississippi River that was abandoned in, I think, the 1730s. And all these curves that you see here are meander scars as the river, the river started as a very small loop and the loop got bigger through time. And this is a process that can be observed happening today. So if you're a farmer on the outside of the bend, you lose land. If you're a farmer on the inside of the bend, you gain land because the water, when this river was active, here's the modern Mississippi there. The water, and this has been measured, it goes faster around the outside of the bend, so it erodes, and it goes slower around the inside of the bed, and it deposits sediment. And as I said, because the Mississippi River and the Ohio River have been surveyed over the last 200 or 300 years, we can measure how fast this process happens. And this particular bar has been cored. These are schematic illustrations of the core because I don't have copyright permission to show the actual cores. But it's this fining upward pattern with trough cross beds at the base going up into current ripples and then mud at the top. And commonly there's roots up here. This is the abandoned channel, which is this. After it gets abandoned, it just fills mainly with mud. And then on the left is a seismic image of a very similar system in the Cretaceous of Alberta, Canada. And so we see the abandoned channel, which is similar to this. It's a little bit smaller. There's 1 kilometer there, and there's a kilometer there. And then we see the meander scars, and this has been cored. And so the cores the sedimentology of the cores is identical to that. And we know the amount of water flowing through here because we see the width of the channel. And the more water flows through a river, the wider the river is. That's what makes a big river. And so there's, limits to the physics of how this works. Now, this is a river that doesn't exist anymore that was heading north. And so this river system has been mapped. It drained as far south as northern Texas. And so in the Cretaceous, everything was draining to the north, kind of the mirror image of the Mississippi today. And so there's no marine fossils in here, it's all terrestrial fossils. And the sedimentology of these units look identical to the sedimentology we see happening today. And we have flume experiments and lots of other experiments that show the limits on how trough crossbeds form, show the limits on how current ripples form. And so that really constrains the depositional conditions. And like here, we see rooting at the top of this. And I've seen some of these cores. And so this is a river system that existed in the Cretaceous. So here's the problem. Beneath this is Devonian limestone. And above this is a couple hundred meters of marine shale. And this is one point bar out of many point bars. So this was this point bar, but you see there's all sorts of point bars that one is cutting into the other. So this is the problem is we see this a lot in the rock record. And so we see that when sea level's high, you get these laterally extensive marine deposits. And then we interpret sea level going down and you get river deposits. And so if you're going to say this isn't a river, then what is it? I mean, the sedimentology is identical to what we see forming today. The morphology is identical to what we see forming today. And it's sandwiched between marine deposits. And there's no marine fossils in here.
To help you engage your point here, Dr. Feldman, how would you respond to a creationist who potentially followed up and asked you the question, are you assuming that because modern rivers, if I'm understanding your point here in the comparison with the Cretaceous river, are you assuming that because modern rivers can produce these features gradually, they cannot be produced rapidly under much higher energy conditions as would be associated with the flood?
So how would you get higher energy conditions? There's a couple ways to do it. One is you need more water flowing through the channel. But the problem there is then you get a bigger channel, and we see the size of the channel. So, you're concerned, and the sediment on either side of the channel is the same as the sediment on either side of this channel. So you're eroding into the same stuff. If it was rock versus sediment, that wouldn't be a fair comparison. And so there's a relationship between the size of the channel and the amount of water flowing through it. Or, when you say amount of water, what we mean is like cubic feet per minute or something like, the water flux.
Are you saying that how much water would flow through it if today's hydrology and assumptions are correct?
Correct. I can't give you that number because I haven't done the calculation, but yeah, the calculation can be done. So if you want to assume that those calculations don't work in the ancient, what are you going to change? You'd have to change the viscosity of water, or maybe the density of water, or the strength of gravity. Right. So these calculations, for example, wouldn't work on Mars because there's different gravity. So we see the same features, but you couldn't back calculate the water flux.
If a flood geologist, whether a proponent of CPT or HPT, and we can hand it to Brian to get his thoughts, if they proposed fundamentally different discharge rates, sediment loads, basin geometry, and hydraulic conditions, couldn't you get those same traits and features with what you're showing in the Cretaceous? It would be similar to what you're comparing with the river in the Mississippi and Ohio, I think you said, but it's occurring rapidly rather than over long periods of time. Dr.
Well, that would violate the sedimentology. So I'm going to turn this light down here. It looks a little bit too bright. Is that better? Yeah, that would violate the sedimentology. So, for example, we see trough crossbeds in the cores through this system. Trough crossbeds, we know how they form. There's a family of conditions under which trough crossbeds would form, and if you have the water going too fast, you won't get trough crossbeds. You just can't. And they're constrained by both the water depth and the velocity and the grain size of the sediment. So the fact that we see the same sedimentary structures places real constraints on the velocity that the water could be going and the depth of the water as well. So yeah, so it's maybe you could get the same geomorphic pattern, but I don't think that would work either, but you certainly couldn't get the same sedimentology.
Is it moving water that creates those crossbeds?
Yes.
Okay, so if you have moving water during the flood, you're saying those same crossbeds can't be formed?
Well, the crossbeds put a limit on the depth and velocity of the water. And so that's the limit that I'm saying. And we've also got the observation that there's no marine fossils in this unit. There's marine fossils below it and above it. And there's soils at the top of the unit. And so when you look at the physical sedimentology of the cores that are through this unit, and this is an area of heavy oil. You've probably heard of the heavy oil in Alberta. And so they drill wells very close together because that's needed to recover the oil. And so we've got lots and lots of cores for this, and all the cores are public. There's a building in Calgary that's a library, and anybody can go look at the cores in this unit. You can interpret themselves. But the physical sedimentology of the sand places limits on the conditions. And so you have to be within those limits. You can't be outside of that, or else you won't get trough crossbeds.
I think it would be helpful for any creationists listening, as I think this discussion will generate a lot of discussion from both young Earth creationists and those that hold to the old Earth plate tectonics model. But could you reiterate what characteristic exactly of the crossbedding itself would uniquely exclude formation by what a flood proponent would say high energy sediment laden currents during the catastrophic flood?
Yeah, this gets very technical, but let me see if I can find a illustration. I just have to look at one of my.
Because I think, as you're looking for that,
I understand what you're asking. I really do understand what you're asking. It's just going to take me a second.
I guess as you're doing that, and we'll shift to Brian too, because I want to get his thoughts. But for my understanding, most flood proponents, whether HPT or CPT, are proposing essentially the same hydraulic principles, but operating under dramatically different flow conditions. And so, instead of me expanding even more on that, Brian, is there anything you want to contribute or add to that before Howard responds?
Yeah, there's a part in the 9th edition. I couldn't find it, but it talks about how the plates gradually, as the water fountains of the Great Deep are bursting up, it's going to slam down, and then pressure is going to build up and it'll burst up again. That's how you get the they call it fluttering in the granite, and he thinks that's how the radioactivity formed. And then it talks about how the plates would gently rise up and then come back down and gently rise up. And that could be what Dr. Feldman's talking about when the sea level rises and falls, or the land going up and down, because that could be, when it rises up and then it drains off and then it comes back down. And then it gets the marine fossils in there, and it rises up and it drains off. And now it's another bed coming down, and then it goes back down. Because I think that, the real challenge is if you got the sea level rising and falling, you still got high tide and low tide twice a day. And that's going to pound on the beach as it rises up, and it's going to pound on the beach as it goes down. I think that as the sea rises every time, it's going to erase any evidence there.
Thank you, Brian.
I tried to share my screen. Did I not do it correctly?
It ended, but I do see it back. Is this what you're looking at? Flow conditions?
Yeah. So first, I'm going to respond to tides. Just because there's tides in the ancient doesn't mean they're very high. If you go to the Pacific Ocean, the tides are typically about that high. And so if you have tides, just because you have two tides a day doesn't mean you're going to erase sedimentologically everything that's there. It depends on how high the tides are. So this is a classic diagram. This is a flume experiment. So this is grain size here. And so these are the standard grain sizes for sand: fine, medium, coarse, very coarse. And then this is the velocity of water. And then this diagram is only valid for 20 centimeters of water depth. And then there'll be a diagram for 30 centimeters and 40 centimeters and a meter and 2 meters and all that. And so trough crossbeds are made by what are called 3D dunes. And so each one of these circles is a flume experiment. So there's hundreds of flume experiments shown in this diagram from 1982. And so if you look at, say, a particular grain size, such as medium sand, you have no movement of sand. And then as the velocity increases, you start getting current ripples. Then you reach a threshold where you get dunes. And then you go up to upper plain beds and A dunes. It doesn't matter what those are. They're just different sedimentary structures. Or you could look at a particular velocity, and as you decrease the grain size, you get different sedimentary structures. And so this is what I mean by it would be a family of conditions. Now, when we look at the ancient, we can measure the grain size. We can look at the sand, put a scale against it, and measure the size of the sand grains. And so we know where we would be on this axis. And then if we find dunes, we say, well, there's a family of velocities. If you're higher than that, you won't get dunes. If you're lower than that, you won't get dunes. So that constrains the conditions under which it forms. Now, it gets a little bit more complicated than that, so I'm going to show one other diagram here. This is part of a YouTube series I'm doing, actually. And so this is the diagram we were just looking at. And what I've done is I've added the dimension of water depth. So how deep is the flowing water? And so then you can see that there's a family of conditions for dunes that changes a little bit as you get deeper water. But there's also a way to use the size of the dunes to very approximately estimate water depth. So if we see dunes which form trough crossbedding, and we know the grain size which we can measure, the dune height, especially if you have a lot of different dunes, the average dune height gives you a very rough estimate of the depth of the water. If you know the depth of the water, you then know the velocity of the water or the range of velocities that'll produce dunes. And we can measure very accurately the direction the water is flowing. And so what you do is you build up a story that constrains the depositional conditions to such an extent there's not much room outside of that is consistent with the data. So that's how and I'm simplifying this a lot from how we actually do it. And this is what I do for a living. So, one of the things I did for Exxon and I do it for other companies is I'll go and I'll use core from a petroleum reservoir, and I'll actually make these measurements in the core and use that to constrain the depositional conditions. And sometimes,
are you saying these are, and you're saying these are based off of hundreds to thousands of flume experiments? And
flume experiments, and then when you get up with really deep water, like this is 100 meters, it's based on river observations. So it's a combination of flume experiments and observations from modern environments. But you're right, thousands of flume experiments. Yep.
And
So
which
like,
okay, well, I'm wondering which specific variable in those experiments measure the millions of years, as in a couple specific variables that tell us that, okay, these cross beds, which are recording sediment transport, require the long period of time and can't be formed rapidly or in a shorter period of time.
that gets a little bit more complicated. We can certainly see how fast the cross beds are forming. So we have that. If there's tidal cycles in a system, we can use that to measure time. And so there are places like there's an outcrop in Kentucky where there's like 200 years worth of tidal cycles in one outcrop. And so we can actually measure the number of years it took to deposit that system by measuring the tidal cycles. But here, to get at the time, we know how fast point bars form. Looking at the previous thing was a point bar. And then if we see a soil on top, there's very rough estimates of how long it takes a soil of a certain thickness of a certain type to form. And so, but just the soil itself means there had to be time for roots and burrowing, insects and all that. And so it's not any one observation to get to the millions of years, but it is a series of very precise observations that get us the depositional conditions, and then putting it in context gets us to the millions of years. But soils, for example, and this point bar I was showing in seismic, that's part of a big river valley system that is preserved in Alberta. It's filled with oil, which is why we know about it. And so that, you put all the pieces together, it's pretty inescapable that you need millions of years. And we know where the sand is coming from. You can identify very precisely the source of the quartz, and we can say, this sand came from Texas, this sand came from the Appalachians, this sand came from the Rocky Mountains by identifying trace minerals and zircon radiometric ages. And so, and we can look at the same age sediments in many different places and then piece together the whole river system that was forming.
I guess my last follow-up question, and I'll have to go back and re-listen to your answer in detail. As you said, it gets more and more technical as more and more questions are asked. And then feel free to answer, let's say in 30 seconds, and then we'll throw it to Brian. And then, to be fair, back to you for a final word, and then we'll move on, because I feel like we can do an entire 3-hour discussion on this, and perhaps we should.
I would love that,
because I think it'd be fun to kind of dig deep onto this. And so my last follow-up question would be, if the same hydraulic conditions occurred during a catastrophic flood, why would the resulting sedimentary structures necessarily look different?
I'm not sure I follow the question. I'm very sorry. So if you had different conditions, you would get different sedimentary structures.
But if you have the same conditions occurring during a catastrophic flood, but they're occurring more rapidly, then I guess I'm trying to understand and help the audience.
But if it's occurring more rapidly, then you're going to go up the scale of velocities, and you'll get different sedimentary structures. So the sedimentary structures puts limits on how fast the water was moving. So it can't be moving more rapidly.
And that's based on the varying velocities. You can tell, because I know you're saying
from flume experiments.
Right. Yeah. From flume experiments, you would get dunes based on a certain velocity, but you'd need a very specific velocity to get that structure versus a different structure.
Correct.
Okay. I see what you're saying.
So as you increase the velocity, you would go from forming dunes. Okay, you stop sharing, but it doesn't matter. You would go from forming dunes to forming upper plain beds and anti-dunes. And so you get different sedimentary structures that represent different velocities. Now, there's a lot of uncertainties here that you have to collect a lot of data to really constrain it. But you constrain it also with the fossils and with the soils and with the overall geometry of the entire deposit. But it does constrain it to the point where you really can't get away from a river.
Are we assuming that during a year-long flood, you have one uniform velocity the entire time? Or could you, during that year-long flood, get a variation of velocities?
That's
those different structures?
That's an awesome question. So what happens when we look at modern rivers is during low flow, when the velocities are very low, not much is happening. And virtually all the deposits are occurring during what's called river flood stage. That's when the water level goes up to the levees. And that's really when the sediment is moving. So what we're seeing when we look at the conditions of the sedimentary structures is we're seeing the kind of once or twice a year floods when almost all the sediment is being moved.
Okay. I
And so
appreciate
the low flow conditions, when you would get other sedimentary structures, those get erased when you get the next flood.
I see. Okay. I appreciate that, Dr. Feldman. Brian, let's throw it to you. If there's anything you'd like to add or contribute, go ahead. Dr. Feldman, quick final word on that one, since we spent a considerable time on it, and then we'll move on. Go ahead.
What was the question that was on the screen that I'm supposed to be responding to?
Well, it generated a much larger discussion on the question of channels and riverbeds and so on and so forth. And so if there's nothing else you want to add to that, Brian.
Well, yeah, I do. But I think the thing had something about accepting things, the whatever. But
I think it was this one right here.
Yeah. How are you not a neutral interpreter if you accept teachings you have not dug into? Okay. And that's basically what we're seeing tonight. We got two worldviews interpreting the same evidence. We got two worldviews. One worldview believes what God said, another worldview doesn't. And so we've got these two worldviews, and based on what you believe, that's going to determine what you see. And the perfect example again is Dr. Ron Neller. He was an evolutionist his whole life until he saw all the evidence and he came to a worldwide flood. And so I found it, I think it was on page 210, where, because he's assuming this uniformitarianism process is the way rivers flow today is the way they've always had to flow. But I think that's an invalid assumption, and it's an arbitrary one. And if you go into page 210 at creationscience.com, you can read about how these plates go up and down. The amplitude, the crust will come out of the water, and then the water could drain off, making riverbeds, and then it could go back down under the water. So then you've got the marine sediments, and then it could come up out of the water. And that's another possibility where you get a different riverbeds there. And I think people should have an opportunity to think. Look at the pros and cons of each theory. It's just, and then come to their own conclusion. And again, I think it's really hurt science when we say my way's the right way. Don't think about anything else.
So I absolutely did not say that rivers today operate the way rivers in the past did. I never made that assumption. I'm using the sedimentology of the sands to constrain the depositional conditions.
Well, couldn't they flow at the different rates during the flood as they're going up and down instead of having the whole sea level?
No, because that would give you different sedimentary structures. What worldview am I using when I constrain the deposits based on flume experiments of the physics of how sand is moved by moving water?
I think you're using your basic assumption is that there was no global flood. No matter what the evidence shows, you're going to say there's no global flood.
That is absolutely not true. There have been many global floods, and these are river deposits in between two global floods.
Well, a flood where the whole earth is underwater.
Never happened.
How do you know that?
We've been through this, Brian, because we see the deposits of shorelines at every different age.
Couldn't that happen after the worldwide flood? Couldn't all those things be built up after?
Okay, so if the Cambrian is after the worldwide flood and we see Cambrian shorelines, when did the flood happen?
Well, can't we have that possibility? To just allow for a worldwide flood sometime in history, because some geologists are coming to that point. It used to be no catastrophes. Now, there's catastrophes, and now it just can't be one catastrophe. It's slowly getting there. And as it just out of hand, out of pocket, just say, no, that thought's not allowed.
I'm not saying out of pocket. I'm saying when we look at the deposits of every single age, we can find where the shoreline was.
Well, how do you know when it began? How did the Earth begin? If it's a molten blob,
well, that's a different,
where did water come
question.
from?
And again, that's not your. Every time we try to get down to one specific point, you try to expand it to the origin of the Earth and the origin of the Big Bang.
I'm talking about worldviews. Worldviews determine what we see. That's what the question was.
I claim that I'm not using a worldview. I'm looking at the evidence. Well, at what point did I use a worldview when we looked at flume experiments? Those are the data that I'm using to interpret the depositional conditions.
Well, you're not say that the plumes. You're not talking the mantle plumes.
Flume.
Are you referring back to the Flume experiments on
So
the river
water
channel
Well, yeah,
topic?
you're assuming that couldn't have happened during a very chaotic worldwide flood that lasted a year or 180 days, and then it drove
I
off.
can prove
8
I can
months.
prove it didn't last. I can prove the flooding didn't last a year because there's outcrops with tidal cycles that cover hundreds of years. And so you
Dr.
can
Feldman,
count-
a helpful question for me as I go back, as I typically like to do with these origins debates we host, I like to re-listen, digest better, and absorb the information and study it as best as I can, especially on these geology topics. In a quick 30-second answer to a layperson, because I think this is an important topic on the river channels and the Flume experiments and your answers there with flow cycles and varying velocities. A follow-up question that I would have is, how do you distinguish between fluctuating flow velocities produced during a catastrophic flood, like Brian is arguing for, and fluctuating flow velocities produced over thousands of years, as you would be arguing for? How do we distinguish between that?
Well, you've got the morphology of the river channel, and then you've got soils on either side of the river channel.
Okay.
So the soils constrain how long it had to have taken, or they put lower limits that you need time for the soils to form, and you can prove that the channels are contemporaneous with the soils.
So if all of this is happening rapidly, you're saying the amount of soils or the morphology would be different?
You wouldn't get soils.
You wouldn't get soils at all.
Yeah.
How come?
Well, if deposition is too rapid, in order for a soil to form, you need to have slow deposition or no deposition, time for rooting, time for wetting and drying of the soils, time for insects to burrow. And so, although when we see a soil, we can't say, oh, that took 2,482 years. You can't say that. But you can say it took decades
longer
or
than a year,
hundreds of years or thousands of years. You can get order of magnitude. And so when you put everything together, it precludes a single year-long global flood. It's not a worldview, it's evidence.
And are those soils that you refer to the paleo soils, the
Yes.
ancient soils?
Yes.
Okay, I see what you're saying.
And I've listened to Michael Ord and other people discuss the cons against the soils, and their complaints aren't consistent with the evidence.
Okay, I appreciate that. Brian, I know there's so much more we could discuss here, but I do want to shift to Scriptures and Stones. He's been patient here. He's got a specific question for you, and he's asking, how would HPT explain why earthquake waves in the eastern U.S. travel farther with more energy than in the western U.S.? He argues plate tectonics can explain this.
Yeah, it's because in the east it's more solid. But in the west, that's where in the west, the Rockies, the North America, if you look on a map, the mid-oceanic ridge runs right into North America. North America slid over the top of the mid-oceanic ridge, so it's broken up into a lot more pieces, so that the earthquake the energy is gonna dissipate. It can't go as far. Where that didn't happen in the Appalachians. So that's more solid. So an earthquake there will go a lot farther because it's not broke, because the Atlantic or the Appalachians didn't slide over the mid-oceanic ridge. There's a lot more what would you call that, activity in the western part of the United States, and that's because it slid over the mid-oceanic ridge.
Thank you, Brian. Anything you'd like to add to that, Howard?
No, he's dead on correct, except for the time frame.
There we go. Okay, well, so some minor agreement there then. So next question here. I think this is a good one too, as it relates to, see if I can find it. Here it is. Creation Bros. So I'm glad that this question came up, because I think it also relates to, and if there's future programs with Mike Ord himself, it'd be fun to engage. And so this is his model, the beds hypothesis, and it does relate to some of the arguments made and points discussed here on trace fossils, but also I think on the paleo soils, which he just discussed. And so he's asking for Howard.
What do you think? I don't know what the beds hypothesis is.
Okay.
Can you describe it?
Yeah, I can explain it. So beds hypothesis, that stands for briefly exposed diluvial sediments. And essentially, it's Mike Ord's way of saying how temporary exposure of freshly deposited flood sediments could account for features like trace fossils, burrows, bioturbation, dinosaur trackways. But in addition, and we'll give you plenty of time to respond, the soil issue, where if those sediments that are deposited, if they're temporarily exposed, that could allow for localized weathering, root activity, burrowing, and then the waters would cover them again. And so I guess the question then, Howard, what are your thoughts on that? Do you think that's a decent explanation for the things you're pointing out?
No. So here's just one example. I mean, to give a full example, full explanation would take a while. But there's a particular type of soil called a vertisol, and it forms in clays as a result of wetting and drying of the clay. So when the clay gets wet, the clay minerals actually expand as they absorb water, and then when they dry, they contract. And this repeated over many, many cycles, like thousands and thousands of cycles, produces certain specific physical characteristics in the soil. And they're called vertisols. They have cracks at certain angles, and they have beds and slicken sides. And there's a progression of features from the top to the bottom. So again, we can't say that this soil, when you see something like that, let's say 2 meters thick, it took exactly this many years. But what we can say is it took thousands of wetting and drying cycles, which probably took hundreds of years. And so and then when we see the different horizonations, there's also associated with vertisols commonly. In modern vertisols, there's minerals that are dissolved at the top and then precipitated at the bottom, and they make very specific types of nodules, and we see those in the ancient. And so when you add on top of that the insect burrows, and roots don't typically get preserved in vertisols, but when you add all the features together, you can't do it in a few days or a few weeks or even a few years. You need decades to hundreds of years. And then you have a stack of vertisols, maybe 10 of them on top of each other. And you need a few years or a few decades for each one. So no, you can't do it in that short a period of time.
Are you using modern analogs to conclude that those are truly mature
Well, it's
vertisols?
partly modern analogs. It's partly just the physics of how long it takes to wet a soil, and then how long it takes for, say, a 2-meter soil to completely dry out, and then to wet it again, and then to dry it out. And so you need many cycles. I'm talking about vertisols in particular. This doesn't necessarily apply to other soils, but you need many cycles of wetting and drying for that to happen. And because rainwater is just slightly acidic, it takes time for the minerals to be dissolved and then to be precipitated at a lower depth. So, again, I can't put a precise number of years on it, but we can say the physics doesn't allow this to happen. You can't wet and dry a soil enough times to get these features in less than in like a year or even a few years, or a few, maybe when you start getting into 100 years, you start getting to the right amount of time, just from how long it takes for the soil to dry after it's wetted.
So you don't think during the year-long flood, fundamentally different hydrologic and geochemical conditions could explain what you're calling the vertisols?
There's certain physical limits to how fast the soil dries. I mean, what are you going to do to make it dry faster? And so, I don't see how. I mean, it would be an amazing coincidence if during this year-long flood we absolutely duplicated perfectly the vast variety of soils we see forming today. We see a lot of different kinds of soils today, and we see those same types of soils in the ancient. And so,
okay, so
so
I guess to the question I asked earlier, you are using the modern soil formation as an analog to what you find in the fossil record sandwiched between these layers to conclude, okay, these are the same types of soils requiring the same types of conditions, basically.
Up to a certain point. Like I say, you can't put, a specific number of years that it takes to produce a soil, but you can put limits on how fast the processes happen.
Okay.
And you need time. Like if there are insects in there, insect burrows. Where do the insects have to come in? They have to reproduce. They have to start digging their burrows with larvae coming out and all that stuff. And so that takes time for all that to happen.
Brian, anything you'd like to add to that?
Yeah, what I think that Michael Ord's bed model there, bed hypotheses, that kind of goes along with what was on page 210, I believe, of In the Beginning, where it talks about those fluctuations, flutter amplitudes, where the plates are coming out of the water and then going back down into the water, and coming out of the water and going back down into the water. And, he had said something, I don't know if he caught it, but he said rainwater's acidic. Well, it's like, well, how does he know what the rainwater is during the flood? It's that uniformitarian perspective, like today is how it's always been. And I would say, no, today isn't how it's always been. So there's two different perspectives. And what's bothersome to me is they don't get to see the other perspective. So if people want to see people who don't believe in plate tectonics, you can go into rsr.org and then it's the titled Plate Tectonics, Subduction Doesn't Work. And then you can get a whole list of PhD scientists who disagree with what Dr. Feldman has been saying. And you can also look into the new concepts in global tectonics, where that's a journal for people that can't get into the mainline journals, kind of like, what was it? Descent from Darwin. Those are PhD scientists who doubt Darwinian evolution. And cosmologystatement.org, where these are astronomers that doubt the Big Bang, and they explain why. And my point is that information should be taught in class. There should be, okay, this is a theory that's taught. This is what people say about the weaknesses. They don't have to promote another theory, but they should at least know that there's people that disagree. I think that would be a small step toward giving people freedom to think.
So when I said rainwater is acidic, all you need for rainwater to be acidic is carbon dioxide in the atmosphere. So if there's carbon dioxide in the atmosphere, some of it's going to be absorbed in the water, and that'll make it acidic. So that's not a uniformitarian assumption, unless you think the atmosphere lacked carbon dioxide.
Okay. Double checking the questions here, gentlemen. I think this has turned into...
How many people are watching, Donnie?
Right now, we got about 40 watching.
Okay.
So Static 412 $2 super sticker. He says, "What if we said plate tectonics couldn't be taught?" He's coming at you, Dr. Feldman. Feel free to
Well,
come right
okay.
back at him.
I can show you lots of places where hydroplate theory contradicts the data. Show me a place where plate tectonics contradicts the data. There are certain things we don't have explained, like the initiation of subduction, although there's some attempts at that. But there's nothing that contradicts evidence. There's no evidence that we have from the Earth today that contradicts plate tectonics. And
Brian,
there's lots of evidence that contradicts hydroplate.
Oh, well, this book right here, I encourage everybody to get it. 20 Reasons to Question Plate Tectonics. You're going to see 20 reasons that it goes against the data.
It's easy to list 20 reasons. It's hard to find any of those reasons that are actually true. I've read that book. I have it right here. See, here it is. I've read it. Well, the lighting is terrible, but I read it. None of those reasons hold up.
None of them. Well, that's because the expanding plates are 3 times bigger, but they just happen to get squeezed into these other plates. That's your, you just hand wave it. Oh, wait, it just went faster into the subductions. So it just got squeezed in there. And if that's what you did with all 20 of them, it's like, I'm skeptical.
Yeah, I'm willing to go through that book point by point. Some of them are absurdly obvious that they're wrong. I mean, it's just really silly. Like one of the complaints is that the transform faults in the oceans disappear as you get closer to the continent. They don't disappear. They're buried by sediment. So, and there's complaints about granite being found on the ocean floor, but those are drop stones from glaciers, and they even have glacial scrape marks on them. So,
Well, it sounds like you're the guru. It has to
I'm
agree
not a
with
guru.
you. There can't be any other interpretation of unless you approve it. Well, what if we made Ron Neller the guru? He's seen it both sides. Why can't
I'm
he
not
be the
saying
guru
I'm the
instead?
guru. I'm saying when these faults go into the subsurface, they're buried by sediment. This is something that can be directly observed.
Well, you're saying kids can't even look at it. They can't think. They have to follow this one
No, I'm not
dominant
saying
theory.
that. I'm saying that it's easy to list 20 reasons why plate tectonics must be false. It's hard to come up with even one that is true. And this is not a worldview. This is objective evidence that says that some of these reasons cannot possibly be true because they are contradicted by evidence. This is evidence, not worldview.
So we're supposed to believe that this spreading 3 times bigger than when it's going in is just going to magically get to the right size to go right in at the right.
It's not the right size. You have to look at the direction and you have to look at the velocity. And when you line up things and you add the velocities, it all works.
It all gets squeezed in there just magically.
The way you're describing it isn't the way you're describing it is not correct.
Well, how does that happen? It's 3 times bigger and it gets squeezed into something that's a third the size. How else would that happen?
It doesn't have to get squeezed in. It just has to go faster.
Well, that's squeezing it in.
No.
How does that happen?
No.
Okay. Well, there's 2 interpretations. And my thing is, let's let kids see both sides. Let journals publish both sides. That's how we're going to get science to advance. But when we exclude ideas because we control the journals, that's hurting science.
Well, I keep saying I don't agree with presenting a theory that violates data that we have and trust.
Well, that's what they said about washing your hands after doing an autopsy. That violated what they were taught. And it took,
just because you can pull out a few examples where scientists got it wrong,
history's full
doesn't
of
mean
it.
that this is wrong. I'm talking about evidence and you're talking about history.
Well, no, I'm talking about dogmatically saying this is the way it is. And I think that's dangerous.
I showed you the evidence. I showed you the evidence of what it looks like for the Mid-Atlantic. What's your interpretation of the earthquake pattern in the Mid-Atlantic Ridge?
Well, I would suggest that it's going towards where the void is, where the deep went in. But Pastor Kevin Lee did an earthquake talk at the Hydroplate conference. Yeah. People can look at that. I don't know, maybe you'd want to look at that if you'd want to see an interpretation of that.
He discusses that specific fault pattern or that specific.
Well, you'd have to watch it and find out if you're interested in seeing how the Hydroplate would explain.
I mean, this was a prediction that was made, and then they collected the data, and it matched the Tectonics prediction perfectly.
Okay, I would like to see that prediction published. I would like to see that.
It was published in 1960. It was published in 1966.
Yeah, send me the link. I'd like to see that.
I gave you the reference in my talk. Well, I did. Why are you laughing? I gave you the reference in my talk. I had it at the top of the page. It had those.
Okay, I'll go back and I'll look at it. I will.
Yeah.
I will, honestly.
I mean,
if there's errors in here, we want to get it fixed. We don't want to be pushing errors.
Except that you don't accept all the errors I've already pointed out.
Well, squeezing something that's 3 times bigger into a third of the size. I'm sorry, I don't have enough faith to believe that.
I'm talking about the shelf edge. I mean, he doesn't.
Well, that's just a rough diagram to get an impression across.
It's not a rough diagram.
Well, in
the figure caption, he says this is typical of a shelf edge around the world, and that is false. He says Africa was reduced by 35%. That is false. It's example after example. He says limestone is produced from the fountains of the deep, and that doesn't explain how chalk is full of fossils. Chalk is made mostly of fossils. And so, there's so many examples.
Can't you allow it? Can't you let the theory be there, and you can let kids see the strengths and weaknesses of each theory instead of saying this is how it is and ignore all those PhDs that disagree with it. And if they do disagree with it, we're going to fire them. Is that how you want science to be?
I don't know anything about firing people, but
I
do understand enough about geology. I read everything he said about petroleum. None of it is true, and we have direct evidence that what he says is false. The idea of preserving petroleum and how it collects, it's just he's wildly inaccurate about that. And this is, what I did for 30, or what I'm still doing for 30 years. And so, no, you can't teach a theory that at its core is based on false information.
Well, having evolution, life coming from non-life is, I believe, false
I'm
information. That's
talking
never
about
been proven, but it's taught as a
You
fact.
keep changing the subject.
Okay, John,
you got
I feel like we're just going in circles now.
Okay.
I feel we've discussed these same points many times, which is good. I think we've officially left no stone unturned. We're over the 4-hour mark on this, what I would call an epic marathon plate tectonics versus hydroplate theory debate. We touched on a lot. As I typically like to say, the audience Q&A helps us to expand even more and make this debate, these debates, that much more comprehensive. So it's a good opportunity to wrap up here. Dr. Howard Feldman, Brian Lauer, excellent endurance. It's over 4 hours and it feels like you guys are ready to go for another 4 hours. So hopefully we can do another one of these in the future. I think it's a great topic with a lot of really interesting subtopics that I feel like discuss for a while too. So anyways, let's get some final words, final thoughts. I had a great time. I hope the audience enjoyed this as much as I did. Dr. Howard Feldman, it is your first official time here on Standing For Truth. I hope you had a positive experience. Let's start with you. Appreciate you doing this. Final words, final thoughts.
Yeah, I object to this whole worldview idea. When I approach an outcrop, I collect data and I use the physics of how sediments are deposited to determine what the conditions are. And it's not really any more complicated than that. And when you do that, the young Earth disappears, a single flood disappears. You're really constrained into an ancient Earth without even using radiometric dates, just using the physics and the processes of how these things form. And I object to teaching theories that at their core are based on false information. And so that's my bottom line. And that's why I wanted to come on and have my say. And I really appreciate you giving me the opportunity. And I really do appreciate that. Thank you.
Well, I appreciate you giving us your time, not only for the debate to the both of you, the 4-hour debate. It doesn't feel like that, but also the time leading up to it, because these are technical topics and they deserve very careful study and research, which you both have done to give us an engaging event tonight. So Dr. Feldman, thank you for those final words, final thoughts.
One more thing. Can I just say one more thing?
Yep.
Yeah. If you do want to organize a field trip to actually look at the rocks, I'd be happy to be involved in that.
Okay, very good. And hopefully before then we can arrange another either debate or type of discussion where we can dig even deeper on these issues. So helps us both positions, I think, engaging these technical points helps us to refine our understanding of not only our own positions, but each other's positions. So Brian, thank you as well for doing this, for the time for the debate, but also the time leading up to it. Final words, final thoughts, Brian?
Well, I'd like to thank Dr. Feldman for doing this. I appreciate you stepping up to the microphone. I wish more scientists would do that. And I think that's what helps science progress. And I would encourage people to go into creationscience.com and you can see this book online for free, or go into rsr.org or Amazon. You can buy it now. And then they've got these decision trees where it's got all the theories on top, and then it's got all the features on the side. And I think that should be in every textbook, and it should be, and people can then look at it. And what happened to my brother-in-law, he had a geology class in college, and they looked at for Grand Canyon, tried to figure out how it worked, looked at all the theories, none of them worked. Then on Friday, the professor said, hey, there's one theory we haven't talked about. Anybody know what it is? Kid raised his hand and said, no, it's flood. He said, you're right, but we can't talk about it. And that type of mindset, now the hydroplate isn't the floodwater draining, understand that, but that type of mindset, excluding anything that'll point to God, is really hurting science. And hopefully we can get freedom to think back in academia. And once that happens, we're going to have a scientific revolution. And so I do thank Dr. Feldman for participating. And my big thing about doing all of this is, creation points to a creator, and the creator revealed himself in a book. And it says what Jesus did for us to pay for our sins. And we pray that people would put their faith in Christ so they can escape the penalty of hell. And we just pray that for anybody watching. This what happened to Ron Neller. I encourage you to listen to his testimony. He studied this for 30 years, and the evidence pointed him to a global flood. And then he said, well, the Bible says there was a flood. Maybe there's a God. And then he went into it, and he actually found that there was a God. And to think we all got here by chance random processes takes way more faith to think than we got here by a creator.
Okay, Brian, thank you very much for those final words and final thoughts. Gentlemen, you essentially gave us a mini course, crash course in geology, plate tectonics, hydroplate, and it was great to see how you both interact with each other's points and models and understanding on these important topics. So Dr. Howard Feldman, Brian Lauer, thank you again for your time. This was a fantastic debate. To the audience, thank you for the support, the engagement, all the questions, challenges, objections that came in made the debate that much more fun because it gave us the opportunity to expand even more on the topic. So, okay, God bless you all. Stand for Truth is signing off. We'll talk to you soon.